Hello there and welcome to Science for Sleep, where curiosity gets cozy, the universe lowers its voice a little, and even the largest structures in existence are allowed to take their time. Tonight, we are going somewhere that may sound, at first, like nowhere at all. We are drifting into the great empty spaces of the cosmos, the vast regions between galaxy clusters and glowing filaments, where there are not many stars, not many galaxies, not much light, and yet, strangely enough, a great deal to learn. This is a journey through every cosmic void type in the universe, from ordinary galaxy voids to enormous supervoids, from small hidden gaps between galaxy groups to strange regions that grow inside even larger emptiness, and from the visible hollows we can map with galaxies to the invisible hollows shaped by dark matter itself. And yes, a video about emptiness might sound like the scientific version of watching paint dry in a very large room, but stay with me. Cosmic voids are not just blank spaces. They are not mistakes in the map, not areas where the universe forgot to put furniture, although that is a tempting way to picture them. They are a real part of the universe's structure. They help shape where galaxies gather, how matter flows, how gravity builds the cosmic web, and how the universe has grown from a nearly smooth beginning into the immense, uneven, web-like place we observe today. In a way, voids are like the quiet spaces between notes in music. Without them, the pattern would not make sense. If every part of the universe were filled equally, there would be no cosmic web, no great walls of galaxies, no filaments stretching across space like long bridges of light, and no huge dark rooms between them where the universe seems to breathe out. Before we go any farther, let me ask you something gently. Where are you listening from tonight? Are you near a window, with the evening outside your room, or somewhere early in the morning with the day just beginning? And if you looked up from where you are, even for a moment, would you be able to see the sky, or are you tucked beneath a ceiling, a blanket, maybe the soft glow of a phone screen? It is a funny thing, isn't it? We are here on a planet crowded with streets, rooms, cups of tea, unread messages, and all the small noise of being human. And yet most of the universe is not crowded at all. Most of it is distance. Most of it is space between things. And tonight, instead of rushing toward the brightest star or the most dramatic black hole, we are going to turn toward the emptiness and ask what it is doing there. If you find this kind of slow journey soothing, or if the thought of enormous cosmic quiet helps your mind settle after a long day, I would be very grateful if you liked the video and subscribed. It helps this little sleepy corner of science reach other people who might also need a calm place to rest their thoughts. And if you are already settling in, eyes heavy, shoulders loosening, then do not worry about catching every detail. Cosmic voids have waited billions of years to be noticed. They can wait a little longer if you drift off somewhere along the way. So, let us begin with the picture. Imagine the universe not as a smooth spread of stars, sprinkled evenly like sugar across black cloth, but as something more like a sponge, or a web, or a very strange loaf of bread full of bubbles. Galaxies are not scattered randomly. They gather in clusters, and clusters gather into superclusters. Between them stretch filaments, long chains of galaxies and dark matter that can reach across hundreds of millions of light years. Where filaments cross, matter piles up into dense nodes, the busy cities of the cosmic web. But between those bright strands lie great open regions, enormous underdense spaces where the number of galaxies drops dramatically. These are cosmic voids. The word void can sound absolute, as if these places contain nothing at all. But in astronomy, nothing is often a little more complicated than it sounds. A cosmic void is not truly empty. It may contain thin gas, faint galaxies, dark matter, radiation, stray particles, and all the quiet background ingredients of the universe, but compared with galaxy clusters and filaments, it is very empty. It is underdense, which means it has much less matter than the cosmic average. If a galaxy cluster is a crowded city centre at lunchtime, a void is a wide rural field at 3 in the morning. There may still be something there, but the difference in activity is hard to miss. Astronomers began to understand these huge empty regions as galaxy surveys improved. Once we could map not just a few galaxies but thousands and then millions, the structure became clearer. The universe on very large scales looked like a network. Galaxies formed walls and strands. Voids filled the spaces between them. At first, this may seem surprising. Gravity pulls matter together, so perhaps we might expect everything simply to clump into lumps. But that is exactly part of the story. In the early universe, matter was not spread with perfect smoothness. Some regions were slightly denser, others slightly less dense. The denser places pulled in more material over time, becoming even denser. The less dense places lost matter to their surroundings, becoming emptier. The rich got richer, in a cosmic sense, and the quiet places became quieter. This means voids are not just empty leftovers. They are active participants in the growth of structure. Their edges can push outward as matter flows away from their interiors and toward denser filaments and clusters. Their shapes can be stretched and squeezed by the gravity of nearby structures. Some voids merge with others, forming larger, emptier regions. Some small voids survive inside larger ones. Others are caught in crowded environments and may eventually be crushed as surrounding matter collapses. So even emptiness has a life story. Not a life in the biological sense, of course. No tiny voids with birthdays and awkward school photographs, but a history, an evolution, a pattern of growth and change. One of the simplest kinds we will meet is the galaxy void, the ordinary large-scale emptiness defined by a lack of visible galaxies. These are the broad, low-density regions that appear in maps of galaxy positions. They can span tens of millions of light-years, sometimes more, and they help create the bubble-like appearance of the cosmic web. In many ways, these are the voids astronomers first mean when they talk about cosmic voids. They are measured by looking at where galaxies are not. That may sound easy, but it is not quite as simple as drawing circles around empty patches. Galaxies have different brightnesses. Surveys have limits. Some galaxies are too faint to detect. Dust, distance, telescope sensitivity, and mapping methods all matter. Finding a void means asking, carefully, how empty is empty enough? Then there are supervoids, the larger cousins of ordinary voids. These can stretch across hundreds of millions of light-years and sometimes appear as enormous underdense regions made of smaller connected voids. A supervoid is not necessarily one perfectly empty bubble. It can be a vast zone where the average density is low, with smaller structures still scattered inside it. Think of a desert. A desert is not completely empty. It may have rocks, shrubs, insects, dry riverbeds, even cities at its edges. But compared with a rainforest, the pattern is sparse. A supervoid works a little like that, except the scale is so large that light itself needs hundreds of millions of years to cross it. If you tried to travel across one at the speed of a spacecraft, well, you would need a calendar with a very optimistic number of pages. There are also smaller voids, sometimes called mini-voids or small voids, depending on the context and the method used to identify them. These can occur between galaxy groups or within the larger structure of the cosmic web. They remind us that emptiness is not found only on the grandest scales. The universe has texture. It has large gaps, medium gaps, and smaller gaps nested among them, like bubbles in foam. A small void may not sound as impressive as a supervoid, but it can be scientifically useful. Smaller voids can tell astronomers how matter behaves in less extreme underdense regions, how galaxies form when they are not crowded by neighbours, and how gravity sculpts the cosmic web at different scales. Now, one of the more interesting ideas in void classification is the difference between void in void and void in cloud regions. The names sound almost like weather reports from a very unusual forecast. Tonight, mostly void in void, with a chance of collapsing void in cloud toward morning. But the idea is genuinely important. A void in void region is a smaller empty region, embedded inside a larger underdense environment. Because the larger region is also underdense, the smaller void can continue expanding and merging with its surroundings. It is emptiness growing inside emptiness. A void in cloud region is different. It is a small underdense patch surrounded by a larger overdense region, a crowded area that is still collapsing under gravity. In that case, the small void may be squeezed, distorted, or even erased as surrounding matter falls inward. So the fate of a void depends not only on what is inside it, but on the larger environment around it. That may feel oddly familiar in a very human way. A quiet person in a quiet room can remain quiet quite easily. A quiet person in the middle of a busy train station has a different experience altogether. The same basic condition, a lower level of activity, can unfold differently depending on the surroundings. Cosmic voids follow a version of this principle. Their future depends on the web around them. We will also talk about dark matter voids, which take us one step deeper. When we map galaxies, we are really using luminous matter as a tracer. Galaxies shine, so we can see them. But most matter in the universe is not shining gas or stars. A large portion is dark matter, which does not emit light but still has gravity. Since dark matter forms the scaffolding of the cosmic web, voids are not only gaps between visible galaxies. They are also regions where dark matter density is lower than average. A place might look empty because it has few galaxies, but the deeper question is how much total matter is there, including the invisible matter we cannot see directly. Simulations help astronomers explore this hidden structure, showing how dark matter flows away from void centers and gathers along walls and filaments. This is one reason voids are useful. Dense regions of the universe are complicated. Galaxy clusters are full of hot gas, mergers, turbulence, black holes, star formation, and all sorts of astrophysical drama. They're fascinating but messy. Voids, by comparison, are cleaner environments. There is less matter, less noise, less interference. That makes them useful for studying big cosmological questions. How does gravity behave on enormous scales? How does dark energy influence the expansion of the universe? How does dark matter shape structure when there is not much ordinary matter around to complicate the picture? A void is not a laboratory in the usual sense. No one has a clipboard floating in the middle of one, checking the temperature and writing, still very empty. But for cosmology, voids can act like natural test regions. Some voids are also close enough, cosmically speaking, to become part of our own neighbourhood story. The local void, for example, is an underdense region near the local group, the small collection of galaxies that includes the Milky Way and Andromeda. Our galaxy is not floating in a simple, even sea. It sits near filaments, groups, flows of matter, and nearby empty regions. These surroundings can influence the motion of galaxies, including our own. Gravity from dense regions pulls, while the relative emptiness of voids changes the balance of motion around them. In a sense, even the empty places near us help shape our address in the universe. There are named voids too, and we will meet some of them later. The Bhutas Void is one of the most famous, a large region discovered in the 1980s that appeared surprisingly empty of bright galaxies. The KBC Void is a proposed large local underdensity connected to debates about how we measure the expansion rate of the universe. There are many catalogued voids found in galaxy surveys, each identified through careful mapping and mathematical methods. Some are famous because they are huge, some because they are nearby, some because they may help test our models of cosmology. But each one is a reminder that the universe is not only defined by where things are, it is also defined by where things are not. That idea can take a moment to settle. We usually pay attention to objects, stars, planets, nebulae, galaxies, black holes. The bright things get names, photographs, headlines, and dramatic music. empty regions do not pose for pictures quite as easily. They are discovered by absence, by statistics, by maps, by noticing that galaxies avoid certain volumes of space. It is a bit like walking into a room and learning something not from what is on the table, but from the chair that is missing, the silence after a question, the gap in a pattern. Voids require us to see structure in absence. That is not always natural for the human mind, but science has a way of teaching us new habits of attention. And perhaps that is why cosmic voids are so fitting for a slow night of thinking. They are enormous, but not loud. They are important, but not flashy. They do not explode, swallow stars, or shoot jets across galaxies. They simply exist as vast, low-density regions, quietly shaping the web of matter around them. They make the universe look the way it does. Without them, the cosmic web would not have its airy architecture. The galaxies would not gather in the same patterns. The large-scale map of everything would lose its contrast, like a photograph with no shadows. When astronomers simulate the universe on computers, voids appear naturally. Start with tiny differences in density in the early universe, add gravity, dark matter, expanding space, and enough time, and the pattern grows. Dense regions collapse into halos and galaxies. Filaments form, walls stretch, voids open between them. The process is not random chaos. It is structure formation. The emptiness is part of the structure, just as much as the clusters are. A sponge is not only the material you can touch, it is also the holes. Remove the holes, and it is no longer a sponge. In the same way, remove the voids, and the cosmic web stops being the cosmic web. So tonight, as we move through this subject piece by piece, we will not treat voids as simple blankness. We will treat them as cosmic environments. Some large, some small, some expanding, some squeezed, some visible through galaxy maps, some inferred through dark matter, some near our own cosmic neighbourhood, and some so large they challenge the imagination even before bedtime has properly begun. We will ask how they form, how they grow, how astronomers find them, what kinds of galaxies live inside them, and why the emptiest places in the universe may help answer some of the deepest questions we have about the whole thing. For now, picture yourself slowly rising away from Earth, past the moon, past the planets, beyond the familiar shape of the Milky Way, until galaxies themselves become points in a vast dark map. At first, you notice the bright gatherings, clusters and chains and glowing knots. But then your eyes adjust and you begin to notice the spaces between. Great roundish hollows, long dim basins, empty regions pressing against one another, separated by thin glowing walls. The universe begins to look less like a box full of stars and more like a living map of density and distance, where matter has gathered along edges and the quiet interiors have opened wide. To understand a cosmic void, really understand it, we first have to loosen our grip on the everyday meaning of empty. Here on Earth, empty usually means a cup with no tea in it, a road with no cars on it, or a fridge that somehow contains only mustard, one lonely carrot, and a feeling of disappointment. Empty is small. Empty is local. Empty is something we can look into and say, yes, there is not much happening there. But in the universe, empty becomes a much stranger idea. It stretches, deepens, and becomes part of the architecture of everything. A cosmic void is not simply a place where nothing exists. It is a region where matter is much thinner than average, where galaxies are rare, where the bright knots of the cosmic web fade away, and where the universe becomes quiet enough for us to notice the shape of absence itself. When astronomers say void, they are not describing perfect nothingness. A cosmic void may contain faint galaxies, thin gas, dark matter, radiation, drifting particles, and the same space-time that exists everywhere else. It is not a hole punched through reality. It is not a tear in the universe. It is not some kind of cosmic storage cupboard where the universe keeps the bits it does not want to deal with. A void is an underdense region, which means it has less matter than the average region of the universe. That is the key. It is not empty in an absolute sense, it is empty by comparison. If a galaxy cluster is a crowded market square, packed with glowing cities of stars, hot gas and dark matter, then a cosmic void is the wide countryside between the towns. You may still find a farmhouse here and there, perhaps a road, perhaps a fence, but the overall feeling is space, distance, and quiet. The universe on large scales is not arranged like stars sprinkled evenly across a dark sheet. It is organised into something astronomers call the cosmic web. This web is made of dense knots, long filaments, broad walls, and the great voids between them. The dense knots are where galaxy clusters live. These are the busiest places in the cosmic map, where hundreds or even thousands of galaxies gather together under gravity. Stretching between those knots are filaments, long bridges of galaxies and dark matter, sometimes running for hundreds of millions of light years. There are also sheet-like walls, huge flattened arrangements of galaxies that border emptier regions, and between all of these structures are voids, the broad low-density chambers that give the web its open shape. It may help to picture soap bubbles in a sink, although on a scale so ridiculous that the sink would need to be larger than imagination, and the bubbles would take light millions of years to cross. In a cluster of bubbles, most of the soapy material gathers in thin films and edges. The interiors are mostly air. The universe is not exactly a foam, of course, because galaxy is not soap, and dark matter has never once offered to help with the washing up. But the image is useful. Matter gathers along boundaries, along threads, along places where gravity has pulled more material together. The voids are the interiors, the regions between those gathered structures. Without the bubbles' interiors, the foam would have no shape. Without cosmic voids, the cosmic web would not look like a web at all. The story begins very early, long before galaxies existed. The young universe was much smoother than it is now, but not perfectly smooth. There were tiny differences in density, little unevennesses left behind from the earliest moments after the Big Bang. Some regions had slightly more matter than average, some had slightly less. These differences were incredibly small at first, but gravity is patient. Over millions and billions of years, the slightly denser regions pulled in more matter. As they gained matter, their gravity became stronger, so they pulled in even more. Meanwhile, the slightly less dense regions lost material to their denser surroundings. Matter flowed away from them, toward the growing filaments and clusters. In this way, voids were not carved out by explosions or swept clean by giant cosmic brooms. They grew naturally as matter drained away from low-density places and gathered elsewhere. This is one of the most important things to understand about cosmic voids. They are not leftover gaps after the universe finished building the interesting parts. They are part of the building process. Their emptiness is connected to the growth of galaxies, clusters, and filaments. A void exists because matter has moved away from it. A filament exists because matter has collected there. The two are partners in the same process. You cannot fully describe the cosmic web by talking only about where matter went. You also have to talk about where matter left. Now, if you could somehow float in the middle of a large cosmic void, the experience would not be dramatic in the way science fiction often likes. There would be no glowing wall marking the edge, no sign saying, "Welcome to the emptiness. Please keep your arms and legs inside the observable universe at all times." You might still see galaxies, but they would be far away and faint, scattered like distant lanterns rather than gathered in bright groups. The night sky from a planet inside a void galaxy might look different from ours, depending on where that galaxy sits and how isolated it is. There would still be stars in that galaxy, and planets, and maybe ordinary local astronomy. But on the grand scale beyond that galaxy, the surroundings would be sparse. The nearest large clusters would be much farther away, than they are in denser parts of the universe. This matters because galaxies do not grow in isolation from their environments. A galaxy in a dense cluster lives a very different life from a galaxy in a void. In clusters, galaxies pass near one another often. They tug each other with gravity, they collide and merge, they move through hot gas. Their star formation can be stirred up or shut down by the crowded surroundings. In voids, galaxies tend to be more isolated. They may evolve more quietly, with fewer close encounters. Many void galaxies are smaller, bluer, and more actively forming stars than large old galaxies in dense regions, although the details can vary. This makes voids useful for studying how environment affects galaxy formation. It is a little like comparing a tree growing in the middle of a busy city street with one growing alone in a wide field. The tree is still a tree, but its surroundings matter. Still, identifying a void is not as simple as pointing a telescope at a dark patch and saying, "There it is." Space is dark almost everywhere. The night sky between stars is dark. The space between galaxies is dark. A cosmic void is found through maps, not through a single photograph. Astronomers need galaxy surveys, large projects that measure the positions and distances of many galaxies across huge volumes of space. Once they know where the galaxies are, they can look for regions where galaxies are missing or unusually sparse. The shape and size of a void depend partly on the survey, the galaxies included, and the mathematical method used to define the empty region. In other words, a void is real, but the exact boundary can be a little fuzzy. The universe does not draw neat circles for our convenience, which is inconsiderate but not surprising. One method is to search for large regions with very few galaxies compared with the average. Another is to use algorithms that trace the cosmic web and find basin-like areas in the density field, places where matter has flowed outward towards surrounding walls and filaments. Some methods define voids as roughly spherical underdense regions. Others allow irregular shapes, because real voids are often stretched, squeezed, joined, or lumpy. A cosmic void can be roundish, but it does not have to be a perfect sphere. In fact, many voids look more like uneven basins or connected hollows than clean bubbles. Their shapes are influenced by the surrounding web. Nearby clusters pull, filaments stretch, hulls press in. The emptiness responds to the matter around it. There is something gentle but important in that idea. Even the emptiest places are shaped by relationships. A void is defined by what surrounds it, by the density around its edge, by the galaxies that trace its boundary, by the matter that has flowed away from its centre. It is not an isolated blank. It is part of a larger pattern. This is very different from how we often imagine emptiness, as a lonely absence. In cosmology, emptiness has neighbours. It has edges. It has history. It has motion. Over time, voids tend to expand relative to the denser structures around them. This does not mean they explode outward like fireworks. It means that as matter continues to gather into filaments and clusters, the low-density regions become even more underdense. Their interiors lose matter, and their boundaries become more defined. In large underdense environments, smaller voids can merge into bigger ones, gradually forming larger empty regions. This is why voids are often described as evolving hierarchically. Small gaps become part of larger gaps. Empty spaces join into broader empty spaces. The universe grows more structured, not only by building denser structures, but by deepening the spaces between them, and yet not every void grows freely. Some small voids form inside regions that are overall dense. These can be squeezed by their surroundings and may eventually collapse or disappear as matter around them falls inward. That is one reason cosmic voids come in different types. Their fate depends on whether they live in a larger underdense region or within a larger overdense one. A void surrounded by more void-like territory has room to expand. A void surrounded by collapsing matter has a harder life. If that sounds unfair, it is. Even emptiness has to deal with the neighbourhood. The scale of these structures is difficult to hold in the mind. A typical cosmic void may span tens of millions of light years. Larger ones can reach hundreds of millions of light years across. A light year is already the distance light travels in 1 year, and light is not exactly known for dawdling. It moves about 300,000 kilometres every second. So when we say a void is tens of millions of light years wide, we're saying that even light, the fastest traveller in the universe, would need tens of millions of years to cross it. A human spacecraft would not cross it in any meaningful human time frame. Your snacks would run out long before the halfway point, and the onboard entertainment system would need to be very, very good. This enormous scale is why cosmic voids can feel almost unreal. We are used to objects. A planet has a surface, a star has light, a galaxy has shape, a black hole has a boundary we can describe. But a void is more like a condition across a huge region. It is a statistical and physical reality, a place where the density is low, where the galaxies are few, where the map opens up. We understand it by comparison, by measurement, by seeing the pattern of where things are and where they are not. The great empty web between galaxies is not empty of meaning. In fact, voids are becoming increasingly valuable in cosmology because they can help test how the universe works on its larger scales. Dense regions are complicated. Clusters are full of messy physics, hot gas, galaxy mergers, energetic black holes, shock waves, magnetic fields, and many overlapping processes. Voids are not simple exactly, but they are cleaner. With less matter inside them, certain effects may stand out more clearly. Scientists study voids to learn about dark energy, the mysterious influence associated with the accelerated expansion of the universe. They also use voids to test gravity, because different theories of gravity can predict slightly different void shapes, motions, and matter distributions. In the quiet places, the universe may whisper clues that are harder to hear in the crowded ones. Voids also connect with dark matter. The galaxies we see are only traces of a deeper matter distribution. Dark matter does not shine, but it has gravity, and it forms much of the scaffolding of the cosmic web. A galaxy void usually corresponds to a dark matter under density too, but the relationship is not perfectly simple. Some small dark matter halos may exist inside voids without forming bright galaxies. Some faint galaxies may be too dim for surveys to detect. This means that when astronomers map voids using galaxies, they are seeing the visible outline of a larger invisible structure. It is like trying to understand the shape of a forest at night by looking only at the windows of cabins scattered among the trees. You can learn a lot, but you know there is more there than the lights reveal. Computer simulations help fill in this hidden picture. Scientists can create model universes with dark matter, gas, gravity, expansion, and initial density variations similar to those inferred from observations of the early universe. Then they let the simulation evolve. Over time, the cosmic web appears. Dense nodes form. Filaments stretch between them. Voids open in between. These simulations are powerful because they show that voids are a natural outcome of our standard picture of cosmic structure formation. They're not surprising once you understand the ingredients. Tiny initial differences plus gravity plus cosmic expansion plus billions of years can make a universe full of vast empty regions and glowing crowded strands. Of course, the word empty still tempts us. It tempts us to imagine a place with no story. But if anything, cosmic voids are places where the story becomes easier to see. In a void, you can study what happens when galaxies grow without constant interruption from crowded neighbours. You can study how matter behaves when density is low. You can study the boundaries where galaxies line up along walls and filaments. You can examine how the expansion of the universe affects large underdense regions. These are not blank pages. They're quieter pages, with fewer words printed on them, which sometimes makes the remaining words stand out more clearly. There is also a strange comfort in knowing that the universe needs emptiness. We often think of emptiness as a lack, something missing, something unfinished. But in the cosmic web, emptiness is structural. It gives contrast. It gives scale. It helps define the crowded places. If galaxies are the beads, voids are the spaces that reveal the necklace. If clusters are cities, voids are the open land that lets us see where the cities end. Without voids, the universe would be more uniform, less textured, less like the grand web we observe. The emptiness is not a mistake. It is part of the design that gravity and time have made from the early universe's tiny uneven beginnings. And this is where the subject becomes quietly astonishing. The largest pattern we know, the arrangement of galaxies across billions of light years, is not simply a pattern of things. It is a pattern of things and spaces together. The cosmic web is made from the bright and the dim, the crowded and the sparse, the gathered and the emptied. When we map the universe, we're not only drawing where galaxies live, we're drawing the great rooms between them. Those rooms have sizes, shapes, histories, and futures. They expand, merge, distort, and sometimes collapse. They influence how matter flows. They help us test our deepest theories. They sit there in the dark, not doing nothing, but doing the quiet work of being part of the whole. So what is a cosmic void, really? It is a vast underdense region in the universe's large-scale structure. It is a place where galaxies are scarce, but not necessarily absent. It is a basin in the cosmic web, a region shaped by gravity, expansion, and the movement of matter over billions of years. It is both an emptiness and an environment. It is not a hole outside the universe, but a low-density part of the universe itself. It is a reminder that structure is made not only by accumulation, but also by separation. Matter gathers here, leaves there, and the contrast between the two becomes the map of everything. Ahead of us, the first kind to examine more closely is the ordinary galaxy void. When we speak about galaxy voids, we are beginning with the most direct kind of cosmic emptiness astronomers can map. Not emptiness in the perfect sense, not a blank outside reality, and not the universe forgetting to finish a corner of the room. A galaxy void is a region of space where galaxies are much rarer than they are elsewhere. That is the simplest way to say it. Astronomers look at the large-scale distribution of galaxies. They notice where galaxies gather into clusters, filaments, and walls, and then they notice the great open regions between them. Those open regions, traced by the absence or scarcity of galaxies, are galaxy voids. They are the ordinary emptiness that fills the cosmos, which sounds contradictory at first, but the universe is rather fond of making simple words behave strangely. Imagine looking at a map of Earth at night, with cities glowing across the continents. You would see bright clusters where people live in dense numbers, thin lines where roads connect towns, and dark stretches where there are fewer lights. The dark regions are not necessarily empty. There may be forests, farms, mountains, animals, rivers, quiet houses, and perhaps someone standing outside wondering why the stars look better there. But compared with the cities, those regions are sparse. A galaxy void works in a similar way, except instead of city lights, we are mapping galaxies, and instead of kilometers, we're dealing with tens of millions of light years. The scale changes so much that the mind has to sit down for a moment and politely ask for a glass of water. These galaxy voids were not obvious when astronomers only had flat pictures of the sky. A telescope image can show thousands of galaxies, but without knowing their distances, it's hard to tell whether they form a real structure or only appear near one another from our point of view. The breakthrough came when astronomers began measuring redshifts for large numbers of galaxies. Redshift gives us a way to estimate how far away a galaxy is, because as the universe expands, light from distant galaxies is stretched toward redder wavelengths. With enough redshift measurements, astronomers could build three-dimensional maps of galaxy positions. And when those maps improved, the universe stopped looking like a random scatter and began looking like a web. Galaxies gathered into long strands and sheets, and between those strands were the voids. That phrase, ordinary emptiness, is useful because galaxy voids are not rare oddities sitting in special corners of space. They are a normal part of the cosmic web. They fill much of the volume of the universe. Most galaxies are found along the denser parts of the web, but much of the space between those structures belongs to voids. It is a little like a sponge. Most of the sponge's volume may be made of holes, but the material around the holes is what gives it shape. If you only describe the sponge by talking about the solid parts, you miss what makes it a sponge. In the same way, if you only describe the universe by listing galaxies and clusters, you miss the great open architecture that gives the cosmic web its form. A typical galaxy void can be tens of millions of light years across. Some are smaller, some are larger, and the exact size depends on how the void is identified. That last point matters. A void does not usually have a sharp wall like a room. There is no physical border where you cross a line and suddenly a sign says, "Now entering low galaxy density, please enjoy the silence." Instead, a void is defined statistically. It is a region where the density of galaxies falls well below the average. The edges are where the density rises again, where galaxies become more common, where filaments and walls begin to take over. Because the cosmic web is irregular, voids can have messy shapes, stretched edges, and smaller structures inside them. Some are roundish, some elongated, some joined to other voids like rooms connected by dark corridors. The simplest way to find a galaxy void is to start with galaxy positions and search for large empty regions. In practice, astronomers use carefully designed algorithms. Some fit large empty spheres between galaxies. Some use watershed methods, almost like imagining the galaxy density field as a landscape, where voids are basins and filaments are ridges. Others use different thresholds for how underdense a region must be. This means one survey may identify voids a little differently from another. That does not make voids imaginary. It simply means nature gave us a flowing, uneven structure, and humans, being humans, have to decide how best to draw boundaries around it. We do the same with forests, mountains, neighborhoods, and biscuits, especially biscuits. The edge is obvious until someone asks for a precise definition. Galaxy voids grow because the universe began with tiny density differences. In the early universe, matter was almost smooth, but not completely. The slightly denser patches pulled in more matter through gravity. The slightly underdense patches lost matter to their surroundings. Over billions of years, denser areas became galaxies, groups, clusters, walls, and filaments. Underdense areas became voids. In that sense, a galaxy void is a fossil of cosmic growth. It shows where matter did not gather, or more accurately, where matter gradually drained away towards stronger gravitational neighborhoods. The emptiness is not passive. It is the other side of structure formation. Think about a crowd in a large hall. If people slowly move toward a stage, the middle front becomes dense, while other parts of the hall become more open. The open spaces did not need to be carved out by someone sweeping people away. They appeared because people moved elsewhere. Cosmic voids grow in a similar way, although the crowd is dark matter, gas, and galaxies, and the stage is the pull of gravity in slightly denser regions. Matter flows toward the cosmic web strands. Voids become emptier by comparison. Their interiors become quieter, while their edges become more defined. Inside a galaxy void, you can still have galaxies. This is important. The name can trick us. Void galaxies exist, and they are scientifically interesting because they live in low-density environments. Some are small, faint galaxies. Some are gas-rich. Some continue forming stars in a relatively undisturbed way. Because they are far from the busiest cosmic neighborhoods, they often experience fewer major interactions with other galaxies. They may not be pulled and stirred as often by close passages, mergers, or cluster environments. So void galaxies can help astronomers ask a simple but powerful question. What does a galaxy become when it grows up with fewer neighbors? That question matters because galaxies are shaped by both internal and external processes. A galaxy has its own gas, stars, dark matter halo, rotation, star formation, and history. But it also has an environment. In a galaxy cluster, a galaxy may be stripped of gas as it moves through hot intracluster material. It may collide or merge with other galaxies. It may have its star formation shut down. In a void, the environment is calmer. There are fewer close encounters and less dense surrounding material. This does not mean every void galaxy is simple, peaceful, or sleepy. Galaxies can always find a way to be complicated, but the lower density setting gives scientists a cleaner place to study certain parts of galaxy evolution. One of the most famous named examples of a galaxy void is the Butter's Void, sometimes called the Great Nothing, which is a name with admirable dramatic confidence. It lies in the direction of the constellation Butter's and was discovered in the early 1980s during surveys of galaxy redshifts. The Butter's Void is so large that it is often discussed as a supervoid, and we will return to that kind of scale later. But it's also a useful example here because it was recognised through the scarcity of galaxies. Astronomers looked into a large volume of space where many galaxies were expected and found far fewer than usual. That is the basic galaxy void idea made famous. Not a place with no universe in it, but a place where the galaxy count drops so sharply that the absence becomes a structure of its own. The Butter's Void is often described as spanning roughly hundreds of millions of light-years, with only a few dozen known galaxies inside a region, where many more would be expected if galaxies were distributed more normally. That image can feel almost unsettling. Imagine being in a galaxy located deep inside such a region. Your own galaxy would still have stars. Your night sky from a planet inside it might still be beautiful. But when your astronomers looked beyond their home galaxy, their maps of the distant universe might reveal an enormous lack of nearby large-scale company. The nearest rich structures would sit far away, beyond a huge low-density gulf. They might not discover the cosmic web in quite the same emotional way we did. They might first learn that they live in a quiet province of space, and only later realise that the rest of the universe is much busier. Another important real example is the local void, which is especially interesting because it sits close to our own cosmic neighbourhood. The Milky Way is part of the local group, along with Andromeda, Triangulum, and many smaller galaxies. Nearby, on one side of our region, lies the local void, an underdense area that helps shape the surrounding galaxy flows. It is not just an empty name on a map, it affects motion. Studies of the local universe show that our local group's movement is influenced by both attraction toward denser regions, such as the Virgo cluster, and the relative expansion away from the emptier local void. In other words, our cosmic neighbourhood is shaped not only by what pulls on us, but also by what is missing nearby. The crowded places tug, and the empty places help define the direction of motion by offering less resistance, less gravity, less matter. That idea is worth resting on for a moment. The local void reminds us that voids are not only distant curiosities, we live near one. Our galaxy is not placed in a perfectly average cosmic environment. We are near dense structures and near underdense ones, near filaments and near emptiness. The universe around us is uneven, and that unevenness matters. It shapes how galaxies move relative to the overall expansion of space. It shapes how astronomers reconstruct the map of nearby matter. It reminds us that our address in the universe is not simply Milky Way, local group, somewhere in space. It is more like Milky Way local group near the edge of a great underdense region, not far from denser cosmic flows. Rather less catchy for a mailing address, but more accurate. A third named region often discussed in the wider void network is the sculptor void, which appears in studies of nearby large-scale structure, and is connected through the broader arrangement of void passages around the local universe. There is also the Hercules void in the larger neighbouring network. These names show that galaxy voids are not isolated circles placed neatly on a diagram. They connect, border one another and form part of a complex underdense network. Just as filaments join clusters, voids can connect with other voids. The empty regions of the universe have passages, boundaries, and relationships, almost like an inverted version of the bright cosmic web. If galaxies form the roads and cities, voids form the open basins between them. This is where ordinary galaxy voids become more than an absence of galaxies. They become a way of understanding cosmic geography. When astronomers map a void, they are not only saying there are fewer galaxies here. They are also saying matter has flowed in certain directions, dense structures have formed around this region, galaxies within it may have evolved differently, and the surrounding web has a particular shape. The void is a clue to the history of movement. It tells us how gravity sculpted the region over billions of years. The ordinary galaxy void also helps us understand why the universe looks similar on very large scales, but highly uneven on smaller large scales. That phrase sounds clumsy, but it matters. On the largest possible scales, if you average over enormous enough volumes, the universe appears broadly homogeneous and isotropic, meaning it has roughly the same average properties everywhere and in every direction. But below that huge averaging scale, it is textured. It has clusters, filaments, walls, and voids. A galaxy void is part of that texture. It may be enormous by human standards, but it is still one feature in the larger cosmic pattern. When galaxy surveys such as the Sloan Digital Sky Survey mapped vast numbers of galaxies, they revealed not one or two voids, but huge populations of them. Catalogues built from these surveys identify many voids across the mapped universe, each defined by the positions of galaxies and the methods used to detect underdense regions. Some catalogued voids are modest in size, some are very large, and many do not have friendly names like Butas or local void. They may be listed in survey catalogues by coordinates, sample names, or algorithmic identifiers. This is one of the funny differences between public imagination and scientific work. We remember the dramatic names, but much of the real work happens among tables, coordinates, redshift bins, selection functions, and quiet rows of data that do not sound nearly as good in a documentary trailer. Still, even the unnamed voids matter. In fact, they may matter more as a population than as individual showpieces. A single famous void can fascinate us, but thousands of voids can teach cosmology. By studying many galaxy voids together, astronomers can measure average density profiles. They can ask how galaxies are distributed from void centers to void edges. They can compare observed voids with simulations. They can test whether our standard model of cosmology produces the right number, size, and shape of voids. They can examine how voids relate to dark matter and dark energy. The ordinary emptiness becomes a statistical tool. The density profile of a galaxy void is especially important. Near the center, the density of galaxies is usually lowest. Moving outward, the density rises. Around the edge, there may be a ridge or wall where galaxies are more common because matter has gathered around the void's boundary. This creates a kind of bowl-shaped pattern in the galaxy distribution. The exact shape depends on the void type, size, environment, and method of identification. Some voids are deeply empty with sharp surrounding walls, others are shallower and less clearly bounded. Some are embedded inside larger underdense regions, while others sit inside more crowded surroundings. That difference will become important when we later talk about void in void and void in cloud regions. Ordinary galaxy voids can also help us think about expansion. The universe is expanding everywhere on large scales, but matter and gravity shape the local details. In overdense regions, gravity can slow expansion, bind galaxies together, and even cause collapse into clusters. In underdense regions, there is less matter to slow the expansion locally, so voids tend to expand relative to denser structures. This is sometimes described as voids growing emptier. The galaxies at their edges are drawn into walls and filaments, while the interiors become more sparsely populated. The void does not expand like a balloon with a neat rubber surface. It expands as a region of low density in an involving cosmic density field. Not exactly a phrase you would embroider on a pillow perhaps, but a lovely thought once it settles. Now, because we are talking about galaxy voids, it is worth asking what would count as a galaxy inside a void. The answer depends partly on the survey. Bright galaxy surveys may miss faint dwarf galaxies. Infrared surveys may see through dust better than optical surveys. Radio observations can detect neutral hydrogen gas in galaxies that may be faint in visible light. So a void that looks nearly empty in one survey may reveal more small or gas-rich galaxies under another method. This does not erase the void. It refines the picture. The void remains underdense compared with the cosmic average, but its interior is not blank. It has a sparse population, like a quiet village spread across a whole county. The Bhuta's void taught astronomers some of this lesson. After its discovery as a striking galaxy-poor region, further searches found galaxies inside it, including galaxies detected through their neutral hydrogen. That did not make the void vanish. It showed that voids are not absolute emptiness. They can contain galaxies, sometimes arranged in thin internal structures, perhaps remnants of smaller filaments, or the marks of how smaller voids merged. This is a useful correction to the imagination. The great nothing is not truly nothing. It is great, certainly. But it contains enough something to keep astronomers busy, which is often how the universe behaves when we try to give it a simple nickname. The local void teaches a different lesson. Because it is nearby, it is not only a feature on a distant galaxy map. It is involved in the motion of our own neighbourhood. Astronomers can use galaxy distances and peculiar velocities, which are motions beyond the smooth expansion of the universe, to infer the distribution of matter and emptiness around us. This is more subtle than simply counting galaxies. It is like watching leaves in a pond to infer currents in the water. Galaxies move in response to gravity. Dense regions attract. Underdense regions shape flows by lacking that attraction. By studying these motions, scientists can reconstruct the invisible geography of nearby space, including the boundary of the local void. This brings us back to the central idea. Galaxy voids are ordinary not because they are boring, but because they are fundamental. They are the common low-density regions of the cosmic web, the spaces between the luminous strands. They are the background architecture that lets the web stand out. They are found by counting galaxies, but they point toward deeper realities: dark matter distribution, gravitational growth, galaxy evolution, and cosmic expansion. In a universe where brightness often gets the attention, galaxy voids ask us to look at what is scarce and take it seriously. There is something very calming about this, at least to me. The universe does not require every place to be crowded in order to be meaningful. Some regions are busy with clusters, hot gas, collisions, and massive galaxies. Other regions are sparse, slow, and widely spaced. Both belong to the same universe. Both carry information. The crowded regions show us where gravity has gathered matter most strongly. The voids show us where matter has moved away, where the cosmic web has opened its great rooms, where galaxies grow with fewer neighbours, and the large-scale pattern becomes visible through contrast. As we drift through the thought of these ordinary galaxy voids, you might picture the cosmic web not from inside a galaxy, but from very far away, as if the whole mapped universe was slowly turning in front of you. There are bright threads where galaxies line up. There are knots where clusters gather. There are sheets and walls, thin but immense. And then there are the voids, the broad open chambers between everything else. Some have famous names, like the Bhuta's void and the local void. Many have only catalogue entries. Some are nearby enough to influence how our own group of galaxies moves. Others lie far away in the survey maps, quiet statistics in a table, each one a low-density basin in the vast cosmic landscape. A supervoid begins with the same basic idea as an ordinary galaxy void, but then the scale grows until the word empty starts to feel much too small for the job. A galaxy void may already stretch across tens of millions of light years, which is large enough to make any human distance look like a dust speck on a dust speck. But a supervoid can reach across hundreds of millions of light years, and in some cases, depending on how it is defined and measured, even more. These are not little gaps between galaxy groups. They are enormous underdense regions of the cosmic web, vast areas where galaxies are unusually scarce across a truly enormous volume of space. If an ordinary void is a quiet room in the universe, a supervoid is a whole quiet wing of the building, with the lights dimmed, the corridors long, and the nearest busy gathering of galaxies very far away. The name supervoid sounds dramatic, and to be fair, it has earned a little drama. We are talking about some of the largest known low-density structures in the universe, but it is worth being careful, because a supervoid is not always one smooth, perfectly round bubble of emptiness. Real cosmic structures are messier than the diagrams we draw to explain them. A supervoid may be a single, very large underdense region, or it may be a connected complex of smaller voids that together form a larger low-density zone. It may have faint galaxies inside it, smaller filaments crossing parts of it, uneven edges, and internal structure. It is not a clean hole cut out of the cosmos. It is more like a huge region where the average matter density is dropped far below the surrounding cosmic web. This matters because the universe does not organize itself with labels attached. There is no point in space where a galaxy void becomes a supervoid and the universe updates the name tag. Astronomers define these categories by scale, density, and method. One survey might identify a huge underdense region as a supervoid. Another might break it into several smaller voids connected along the same line of sight. The difference does not mean one survey is wrong and the other is right. It means the cosmic web has texture, and our maps are attempts to describe that texture with human tools. When the structure is hundreds of millions of light years wide, even the act of drawing a boundary becomes a serious scientific decision. Supervoids grow from the same early cosmic unevenness that made ordinary voids, clusters, and filaments. The young universe began almost smooth, but not perfectly. Tiny density differences were present from the beginning, small variations in where matter was a little thicker or a little thinner. Over time, gravity amplified those differences. Matter flowed toward the denser regions, where galaxies and clusters eventually formed. The less dense regions lost matter to their surroundings, becoming emptier as cosmic history unfolded. In very large, underdense regions, this process can happen across a wide area, allowing many smaller low-density patches to merge into something much larger. The result is a supervoid, an enormous valley in the matter distribution of the universe. Picture a landscape after rain with water running downhill. The water collects in the lower channels, carving streams and rivers, while the higher ground becomes drier. Now reverse the image a little. In the cosmic web, matter flows toward the gravitational low points, the denser regions, while voids become the places that matter leaves behind. A supervoid is like a very large high plain that is drained toward many surrounding valleys, except the landscape is three-dimensional. The flowing material includes dark matter and galaxies, and the rainstorm has been going on for billions of years. So perhaps not exactly like a rainy afternoon, but close enough for a sleepy universe. Because supervoids are so large, they can influence how we think about the universe on its grandest scales. They sit near the boundary between ordinary large-scale structure and the question of cosmic uniformity. Cosmology is built on the idea that if we zoom out far enough, the universe becomes statistically smooth. Not smooth in every small region, of course. We have galaxies, clusters, filaments, voids, walls, and all the large structures we have been discussing. But averaged over very large distances, the universe should not have one side wildly different from another. Supervoids test that idea. They ask, how large can a natural underdensity become in our standard picture of the universe? At what point does a structure become unusually large? And if something appears too large or too empty, Is it really a problem for cosmology, or are we simply looking at a rare but possible part of the cosmic pattern? One of the most famous examples is the Bhuta's Void, often nicknamed the Great Nothing. It lies in the direction of the constellation Bhutas and was first identified through galaxy redshift surveys in the early 1980s. The Bhuta's Void is commonly described as one of the largest known voids in the nearby universe, and because of its scale, it is often placed in the supervoid category. The reason it became famous is simple and striking. Astronomers found far fewer galaxies there than expected. This was not a small empty patch between a few galaxy groups. It was a large region where the galaxy count dropped so sharply that the emptiness itself became the discovery. The nickname Great Nothing is memorable, but it can mislead us if we take it too literally. The Bhuta's Void is not absolutely empty. Later observations found galaxies inside it, including galaxies that are faint or gas-rich. But compared with the number of galaxies expected in a region of similar size, it is sparse. That is what makes it important. A supervoid is not judged by whether it contains 0 galaxies. It is judged by how much lower the density is compared with the cosmic average. In the same way, a desert is not defined by having no life at all. It is defined by being much drier and less densely vegetated than other environments. There may still be plants, insects, animals, and the occasional very stubborn shrub. The desert remains a desert. The void remains a void. Now imagine living in a galaxy inside a region like the Bhuta's Void. Your local galaxy might feel perfectly normal from within. Stars would shine, planets might form. Civilizations, if they existed, could look up and see their own galaxy's stars across the night. But when their astronomers began mapping the larger universe, they would find themselves in a sparse neighborhood. The nearest rich galaxy clusters might be far away. The surrounding sky, in terms of a large-scale galaxy distribution, would look unusually quiet. Their first maps of the cosmos might make the universe seem lonelier than it actually is on average. It is a reminder that where you live in the cosmic web can influence the first impression the universe gives you. Another famous supervoid is the Eridanus supervoid, often discussed because it lies in the direction of the cosmic microwave background cold spot. The cosmic microwave background, or CMB, is the faint afterglow of the early universe, radiation released when the universe became transparent about 380,000 years after the Big Bang. It is mostly extremely uniform, but it has tiny temperature variations across the sky. One region, known as the cold spot, appears colder than expected over a fairly large patch of sky. For years, scientists have debated whether a large underdense region along that line of sight could help explain it. The Eridanus supervoid has become part of that discussion. The idea is that light from the CMB passing through a huge void can be affected slightly by the changing gravitational landscape of the expanding universe. This is connected to what is known as the integrated Sachs-Wolfe effect. We do not need to wrestle that phrase too hard before sleep, but the general idea is manageable. As light travels through large cosmic structures, it can gain or lose tiny amounts of energy depending on how gravitational potentials evolve while the universe expands. A large void can leave a small cold imprint on the CMB. The question is whether the Eridanus supervoid is large and deep enough to explain the full cold spot. Some studies have found evidence for a significant underdensity in that direction, while others have argued that the void structure is not sufficient to account for the entire anomaly. So the Eridanus supervoid is real as a large underdense region, but its role in explaining the cold spot is still treated with care. That kind of careful uncertainty is important. Science does not become weaker when it says, "We know this part, but not that part." In fact, that is where science is most honest. It would be tidy to say the Eridanus supervoid fully explains the cold spot and then neatly close the notebook. But the universe often refuses tidy answers. The supervoid may contribute to the observed cold region, but it may not be the whole explanation. The cold spot could involve statistical chance, primordial conditions, line of sight structure, or a combination of factors. Astronomers continue to study it with galaxy surveys, gravitational lensing maps, and simulations. It remains one of those cosmic questions where the emptiness is not just empty, but interestingly suspicious. Then there is the KBC void, named after Keenan, Barger, and Cowie, who studied evidence for a large local underdensity. This proposed structure is especially intriguing because it involves our own broader cosmic neighbourhood. The idea is that the Milky Way and surrounding galaxies may lie inside a very large region that is less dense than average on scales of hundreds of millions to perhaps over 1 billion light-years, depending on how the structure is defined. This matters because if we live in a large underdense region, it could affect some local measurements of cosmic expansion. In simple terms, a local underdensity can make nearby galaxies appear to move away a little differently than they would in a perfectly average region. That is why the KBC void is sometimes discussed in relation to the Hubble tension, the disagreement between different methods of measuring the expansion rate of the universe. Again, the careful word is discussed. The KBC void is an active topic of debate, not a magic key that instantly solves everything. Some researchers argue that a large local underdensity could reduce the tension between local and early universe measurements. Others argue that the proposed void may not be large enough, deep enough, or compatible enough with the standard cosmological model to explain the full discrepancy. And so the KBC void sits in a fascinating place. It is not only a map feature, it is part of a larger argument about what kind of universe we live in, and whether our local cosmic environment is more unusual than we assumed. This is one reason supervoids feel different from smaller galaxy voids. Their size makes them cosmologically loud, even though they are quiet places. A small void can teach us about galaxy formation and local structure. A supervoid can raise questions about the large-scale distribution of matter, cosmic expansion, the CMB, and how representative our neighbourhood really is. When emptiness becomes large enough, it begins to press against the assumptions we use to understand everything. Still, we should not imagine supervoids as impossible violations of cosmology. The standard model of the universe does produce voids and supervoids. Large underdense regions are expected in a universe where structure grows from early density fluctuations. The debate is usually about details: how large, how deep, how common, how connected, and how likely a particular observed supervoid is. A very large void may be rare, but rare things happen in a universe with an enormous amount of space. If you roll enough cosmic dice, eventually you get some unusual patterns. The tricky part is deciding whether a structure is merely rare or genuinely surprising. One challenge is measurement. To map a supervoid, astronomers need distances to huge numbers of galaxies across a wide area of sky. Spectroscopic redshifts are precise but expensive to gather for millions of galaxies. Photometric redshifts, estimated from galaxy colours, can cover larger samples but have larger uncertainties. Those uncertainties can blur structures along the line of sight. A supervoid may look smoother, deeper, or more connected depending on the data. Dust in our own galaxy can obscure parts of the sky. Survey limits affect which galaxies are detected. Faint galaxies may be missed. Bright galaxies may trace the density field differently from dark matter. So the map of a supervoid is always part observation, part statistical reconstruction, and part careful interpretation. Gravitational lensing can help. Even though dark matter does not shine, its gravity bends light. By measuring tiny distortions in the shapes of distant galaxies, astronomers can infer the mass distribution between us and those galaxies. This allows them to test whether a region that appears underdense in galaxies is also underdense in total matter. For a supervoid like the Eridanus supervoid, lensing studies can provide an independent check on whether a large mass deficit exists in the direction being studied. This is one of the reasons modern surveys are so powerful. They do not only count lights, they measure the invisible weight of the universe. Supervoids also affect galaxy evolution, though in a slower and more statistical way. Galaxies inside or near supervoids tend to live in low-density environments. They may experience fewer mergers, fewer close interactions, and less environmental stripping than galaxies and clusters. Some may remain gas-rich and continue forming stars for longer. Others may be small, faint, and difficult to detect. The outskirts of supervoids, where density rises into walls and filaments, can be especially interesting. There, galaxies may line up along the boundaries, tracing the edges of the empty region. The supervoid is not just a hollow centre. It is also the structure around the hollow, the transition from sparse interior to denser cosmic web. You might picture a supervoid as a vast basin. At the centre, the galaxy density is low. Moving outward, the density rises. Around the edges, galaxies collect in sheets, filaments, and clusters. The boundary is not a hard wall, but it is still meaningful. Matter has flowed away from the interior and toward the surrounding structures. In the long history of the universe, that flow has made the void emptier and the web brighter. The supervoid is the wide basin left behind by this slow, gravitational rearrangement. The size of a supervoid can make time itself feel different in the imagination. Not because time literally changes there in some dramatic science fiction way, but because crossing such a region with light takes so long. If a supervoid is hundreds of millions of light years across, then light entering one side may not leave the other for hundreds of millions of years. During that crossing, stars are born and die, galaxies rotate, planets form, entire branches of life on some distant world, if they exist, might rise and vanish, while a photon is still making its way across the emptiness. That is not poetic exaggeration. That is simply what scale means in the universe. Space is so large that even light has to be patient. At bedtime, that thought can be strangely calming. A supervoid does not hurry. It does not erupt or flicker. It grows through the slow movement of matter over cosmic time. It is an enormous absence created by billions of years of gravity doing exactly what gravity does. The bright places gathered, the dark places opened, and from those simple beginnings came the immense pattern of clusters, filaments, walls, and voids that fills the observable universe. But supervoids also warn us not to trust our instincts too quickly. When we hear that a region is nearly empty, we may imagine it as irrelevant. When we hear that it contains fewer galaxies, we may imagine it has less to say. Yet supervoids are among the most useful structures for asking some of the biggest questions. They help cosmologists test whether gravity behaves as expected on enormous scales. They help probe dark energy, because the expansion of the universe affects the evolution of large underdense regions. They help test the relationship between galaxies and dark matter. They help us ask whether our local universe is typical or unusual. The emptiest regions may turn out to be some of the cleanest places to study the rules of the whole cosmos. This is one of those quiet reversals science often gives us. The crowded places are spectacular, but complicated. Galaxy clusters are full of hot gas, dark matter, merging galaxies, active black holes, and tangled astrophysical processes. Supervoids are not simple, but they are cleaner in some ways. With less matter inside them, certain cosmological effects can stand out more clearly. It is like trying to hear a distant sound. In a busy street, the noise gets lost. In a quiet field, the same sound can travel to you more gently. Voids are the quiet fields of cosmology. Supervoids are the enormous quiet fields. As we drift through the idea of supervoids, it helps to keep 3 examples in mind, each teaching a different lesson. The Buddha's void shows how a vast galaxy-poor region can become famous because the absence is so striking. The Eridanus supervoid shows how a huge underdensity can connect to questions about the CMB and the early universe, while still leaving room for scientific debate. The KBC void shows how a possible local supervoid can become part of discussions about cosmic expansion and whether our neighbourhood is typical. These examples are not identical. They are different kinds of large underdense regions, measured in different ways, used in different scientific arguments. Together, they show that supervoids are not just bigger voids. They are cosmic environments large enough to become cosmological questions. And still, even after all that, the simplest image remains useful. A supervoid is emptiness grown wide. It is a region where the universe has fewer galaxies than expected, less matter than average, and a scale large enough to make the surrounding cosmic web feel like a shoreline around a dark inland sea. It is not nothing. It is not outside the universe. It is not a mistake. It is a vast underdense province of the universe's large-scale structure, shaped by gravity, expansion, dark matter, and time. After travelling through ordinary galaxy voids and then widening our view into supervoids, it might feel a little strange to make the universe smaller again. Smaller, of course, is a very generous word here. We are still talking about regions of space so large that light needs millions of years to cross them. Nothing about a cosmic void is small in the way a cup, a room, or a missing sock is small. But compared with the great supervoids that stretch across hundreds of millions of light years, there are smaller underdense regions tucked into the cosmic web like quiet pockets between busier neighbourhoods. These are sometimes described as small voids, mini-voids, subvoids, or smaller voids inside the larger hierarchy of cosmic structure. The exact words can vary depending on the study, the survey, and the method used, because the universe did not submit a neatly typed classification chart before forming. Rather inconsiderate, but we work with what we have. A small void is still a region where galaxies are scarce compared with the average. It is still part of the cosmic web. It is still shaped by the same slow, gravitational story that makes larger voids. The difference is scale and setting. Instead of a vast, underdense province spanning a huge section of the universe, a small void may sit between galaxy groups, between modest filaments, or inside a larger low-density region. It may be one hollow among many, a little basin in the great uneven landscape of matter. If a supervoid is a wide, quiet sea, then a small void is more like a quiet lake between hills. Still wide, still deep in its own way, but part of a finer pattern. This is important because the cosmic web is not built from only one size of structure. It has layers. Galaxies gather into groups, groups into clusters, clusters into superclusters, and these are connected by filaments and walls. The voids between them also come in layers. There are large voids and smaller voids, broad underdense basins and little hollows, connected empty regions and isolated gaps. In some places, faint galaxies and small groups divide what first appears to be one larger void into several smaller ones. In other places, smaller voids merge over time and become part of a larger expanding emptiness. The universe has a kind of hierarchy, not a ladder with neat rungs, but a branching pattern, where structure appears inside structure, and emptiness appears inside emptiness. You can think of it like looking at a sponge very closely. From far away you might notice only the biggest holes. Move closer, and you see smaller holes inside the walls between the larger holes. Move closer again, and the texture becomes more complicated. The cosmic web is not exactly a sponge, because sponges do not usually contain dark matter, expanding space, and galaxies with supermassive black holes in their centres. At least not the sponges in my kitchen. But the idea helps. The universe has a porous pattern. Voids are not only giant bubbles, they also appear as smaller spaces between the strands and clumps of matter. Mini-voids and small voids are especially interesting because they live closer to the scale of galaxy groups. A galaxy group is a modest gathering of galaxies bound together by gravity. The local group, our own cosmic household, contains the Milky Way, Andromeda, Triangulum, and many smaller dwarf galaxies. It is not as crowded or massive as a galaxy cluster, but it is not isolated either. Across the universe, galaxy groups are common. They are like towns in the cosmic web, smaller than the great cities of clusters, but still important places where galaxies interact, orbit, merge, and evolve. Between these groups, there can be smaller underdense regions, places where the galaxy count drops and the web opens into quieter pockets. These small voids can be hard to identify, because the smaller the structure, the more sensitive it becomes to how we map it. Large supervoids stand out across huge surveys, even if their boundaries are debated. Small voids require detailed data. If your survey misses faint galaxies, a region may look emptier than it really is. If you include more dwarf galaxies or gas-rich galaxies, that same region may reveal a hidden population. If your distance measurements are uncertain, a small gap may blur into its surroundings. In other words, finding a small void is a bit like trying to hear a soft sound in a room where someone keeps moving the furniture. The sound is there, but you need patience, care, and good instruments. Astronomers search for small voids using galaxy positions, redshift surveys, simulations, and sometimes motion data. A galaxy map may reveal where brighter galaxies are missing, but the true matter distribution also includes dark matter and faint objects. This is why small voids are not just observational features, they are also theoretical tests. Simulations of structure formation produce voids on many scales. If our model of dark matter, gravity, and cosmic expansion is correct, then the population of small voids should roughly match what surveys find once observational limits are accounted for. If there are too many small voids, too few, or if their properties differ from predictions, that might tell us something about how structure forms. There is a gentle but serious point here. The small things in cosmology, though still enormous, can be just as informative as the large ones. A supervoid may impress us because it is vast. A mini-void may matter because it is common, numerous, and sensitive to detail. Large structures show the broad architecture of the cosmos. Small voids show the texture. They tell us whether the web is smooth or ragged, whether low-density regions merge cleanly or remain divided by small filaments, whether faint galaxies populate places once thought empty, and how matter behaves on the quieter scales between groups. One reason small voids form is that matter does not flow in one simple direction everywhere. The cosmic web is a complicated gravitational landscape. Some regions pull strongly, some weakly. Matter moves toward denser areas, but the paths are shaped by nearby groups, filaments, and walls. Between two or more galaxy groups, there may be a region where matter has drained away toward those groups, leaving a smaller underdensity behind. That underdensity may expand if it is surrounded by a larger low-density environment, or it may be squeezed if it sits inside a broader collapsing region. Its future depends on the neighbourhood. This is where small voids start to connect naturally with the next idea we will explore later, the difference between voids that grow inside other voids and voids that are crushed by surrounding density. For now, it is enough to notice that small voids are not all the same. A small void between loose galaxy groups in a quiet environment may be gently expanding, becoming emptier as matter continues to flow away. A small void trapped between denser structures may be temporary, distorted or shrinking as matter gathers around it. In the cosmic web, size is not destiny. Environment matters. This may sound familiar from everyday life. A little patch of quiet in a quiet house can remain peaceful for a long time. A little patch of quiet in the middle of a train station is likely to be interrupted. The quietness is real in both cases, but the surroundings decide how long it lasts. A small void behaves in a cosmic version of that idea. Its underdensity is real, but the larger density field around it determines whether it grows, merges, collapses, or becomes stretched into a strange shape along the web. Small voids also help reveal the role of faint galaxies. In the early days of void studies, astronomers often used brighter galaxies because those were easier to detect across large distances. Bright galaxies are useful tracers, but they are not the whole population. As surveys improved, fainter galaxies could be added. And when fainter galaxies are included, some large empty regions become subdivided into smaller voids. The bright galaxies may outline a big gap, but the faint galaxies trace smaller details inside it. The emptiness becomes more textured. What looked like one large room may turn out to contain partitions, side rooms, and a few very quiet residents. This does not mean the void disappears, it means the definition becomes richer. A region can be underdense in bright galaxies, but contain faint galaxies. It can be underdense in ordinary visible matter, but still contain dark matter. It can be empty compared with a cluster, and busy compared with the deepest center of a larger void. Emptiness is relative, and small voids make that relativity very clear. They remind us that when we ask whether a part of the universe is empty, we must also ask empty of what, compared with where, and measured by which tracer. That last word, tracer, is one astronomers use often. Galaxies trace the underlying matter distribution, but they do not trace it perfectly. Dark matter forms the gravitational scaffolding. Gas follows pressure, cooling, heating, and feedback from stars and black holes. Galaxies form only in certain dark matter halos and shine in ways that depend on their histories. If you use only the brightest galaxies, you trace one version of the cosmic web. If you use fainter galaxies, you see more detail. If you use hydrogen gas surveys, you may find gas-rich galaxies that optical surveys miss. If you use gravitational lensing, you can infer the unseen matter. Small voids sit right in the middle of this challenge because they can change appearance depending on what tracer you choose. This is one of the reasons they are scientifically useful. A small void is not just a smaller copy of a big void, it is a test of how galaxies populate the web. In the language of cosmology, it helps connect luminous matter with dark matter. In gentler terms, it helps us compare the universe we can see with the universe that is quietly pulling on everything from behind the curtain. If a region has few bright galaxies but a significant dark matter presence, that teaches one lesson. If it has little luminous matter and also very little dark matter, that teaches another. The difference matters because it tells us how well galaxies reveal the true shape of matter. Some studies of nearby voids show just how subtle this can be. A region that looks underdense in a redshift survey may not be equally underdense when studied through galaxy motions and dynamical information. Galaxy counts tell us where visible galaxies are. Motions can tell us how gravity is acting, and therefore where mass, including dark matter, may be distributed. This means a small or nearby void can appear empty in one sense, but less empty in another. That might sound inconvenient, but it is actually useful. The disagreement, when it exists, becomes information. It says look more carefully, count the galaxies, yes, but also follow the motions. Ask what the invisible matter is doing. Nearer small voids are especially valuable because astronomers can study them in greater detail. The closer a void is, the easier it is to detect fainter galaxies inside and around it, measure distances more carefully, and study galaxy motions. Nearby voids can become laboratories for understanding the relationship between environment and galaxy properties. They also help us reconstruct the local cosmic web, the arrangement of groups, filaments, and empty regions around the Milky Way. Our local universe is not just a smooth, expanding cloud of galaxies. It is a lumpy, flowing, structured region with nearby groups, clusters, filaments, and voids all influencing one another. The local void, which we mentioned before, is not exactly a mini-void in the usual sense, but it helps us understand why smaller underdense regions matter nearby. Around the local group, galaxies are not moving only because the universe expands. They also have peculiar velocities, extra motions caused by the uneven gravitational pull of nearby matter. Dense regions like the Virgo cluster help attract galaxies. Underdense regions help shape motion because there is less gravity coming from that direction. Smaller nearby voids and underdense pockets can contribute to the full pattern of local flows. The universe around us is a map not only of positions, but of movements. There is something almost practical about that, as if voids are part of the traffic system of the cosmos. Matter flows away from underdense regions and toward denser ones. Galaxies drift, fall, and gather along the gravitational roads. Small voids mark the quieter side streets, the places where traffic thins out. They may not have the grand fame of the Bhuta's void, but they are part of how the cosmic traffic pattern is organised. And if you want to understand the whole network, you cannot study only the highways. Small voids may also tell us about the early universe. Since the cosmic web grew from tiny density fluctuations, the number and properties of voids at different scales carry information about those beginnings. A universe with different dark matter properties, different initial fluctuations, or different gravity might produce a different small void population. For example, certain alternative dark matter models can affect the abundance of small structures. Modified gravity models can change how voids expand or how matter clusters around them. These differences may be subtle, but small voids are numerous, and large populations can reveal patterns that one famous structure cannot. This is where a quiet, scientific truth comes in. Sometimes the most powerful evidence does not come from the most dramatic object, it comes from statistics. A single strange void can be exciting, but thousands of smaller voids can become a measuring tool. Their sizes, shapes, density profiles, galaxy populations and environments can be compared with simulations. If the observed universe and the simulated universe match, our model gains support. If they differ, something may be missing. The small voids become little tests placed throughout the cosmic web. Little, again, being a word doing heroic work. Inside these smaller voids, the galaxies that do exist may be especially informative. Void galaxies often tend to be more isolated than galaxies in dense environments. Many are late-type, gas-rich and still-forming stars, though there are exceptions. Their lives can be quieter because they experience fewer close encounters. A galaxy in a cluster may be jostled, stripped, merged, or transformed by its neighbours. A galaxy in a small void may evolve more independently, shaped more by its own internal gas supply and dark matter halo than by constant outside interference. It is not untouched, but it is less crowded. This helps astronomers separate the effects of nature and nurture in galaxy evolution. What comes from the galaxy itself, and what comes from the neighbourhood? A small void hidden between galaxy groups can therefore be a very useful environment. At its edges, you may find galaxies influenced by nearby groups or filaments. Deeper inside, you may find more isolated systems. Comparing these galaxies gives a way to measure how environment changes galaxy behaviour. Are galaxies closer to void edges more massive? Are they redder or older? Are galaxies deeper in voids more actively forming stars? How does gas content change? How do dwarf galaxies behave? These questions may sound narrow, but together they help explain why galaxies across the universe look so different. There is also the question of shape. Small voids can be stretched by surrounding structures. If two galaxy groups pull matter in different directions, the underdense region between them may become elongated. If a filament forms along one side, it may create a sharper boundary. If faint galaxies trace a thin internal bridge, the void may be split into two smaller basins. Real voids are often not smooth spheres. They're irregular, evolving regions. Their shapes preserve information about the forces around them. In the same way that a shoreline tells you something about waves, tides, and rock, a void boundary tells you something about the gravitational environment that shaped it. Small voids also remind us that cosmic structure is not finished. The universe is still evolving. Galaxies still move, groups still merge, filaments still feed clusters, voids still expand or change shape relative to their surroundings. On human timescales, this all appears frozen. We cannot watch a void grow in an evening, which is perhaps good, because it would be a very slow evening indeed. But over cosmic time, these structures evolve. A small void may merge into a larger void. A small underdense region in a crowded area may be squeezed away. A faint filament may form a new boundary. The web is not a static picture. It is more like a very slow motion process, so slow that our entire recorded history would pass between barely noticeable frames. Because small voids are so sensitive to details, they are also affected by how galaxies are selected. A survey that observes only bright red galaxies will find a different void pattern from a survey that includes faint blue galaxies. Bright red galaxies often live in denser environments and trace the larger structures strongly. Faint blue galaxies may appear in less dense regions and divide voids into smaller parts. So a void catalogue is not just a map of the universe. It is also a map made through a particular observational lens. Scientists know this and account for it, but it is important for understanding why void sizes and numbers can differ between studies. This is not a weakness. It is part of the process of learning. The more ways we map the universe, the more complete the picture becomes. Bright galaxies show one skeleton. Faint galaxies add finer bones. Gas surveys show hidden reservoirs. Lensing traces dark matter. Simulations connect them all. Small voids are where these layers often become visible, because they sit close to the limits of what our surveys can distinguish. They ask our maps to be honest. One nice way to think about mini-voids is as the fine print of the cosmic web. The giant structures are the title and main paragraphs. Superclusters, filaments, and supervoids announce the broad story. But the fine print tells you how the story actually works. It contains the exceptions, the conditions, the details that matter when you want the full meaning. Small voids tell us how the cosmic web breaks into smaller patterns, how galaxy groups are separated, how faint galaxies fill or divide empty regions, and how underdense regions behave in different environments. If we could fly through one of these smaller voids, the journey would still be overwhelmingly long. We might pass no large galaxies for millions of years of light travel. We might see a faint dwarf galaxy here, a small spiral there, perhaps a lonely gas-rich system continuing to form stars in a quiet pocket of space. The edges would not appear suddenly. Slowly, gradually, galaxies would become more common. A small group would appear ahead, then a thin filament, then perhaps a brighter wall where matter has gathered. The void would not announce itself with a boundary. It would fade into the surrounding web. Like many real things in nature, it would be clear in the pattern, not in a single sharp line. That is why these smaller voids are hidden. Not because they are invisible in principle, but because they require the right scale of attention. Look too far out, and they blend into larger structures. Look with too few galaxies, and they may appear larger or emptier than they are. Look only at the bright traces, and you miss the small details. But with careful surveys and simulations, the hidden gaps between galaxy groups begin to appear. They are the small pauses in the cosmic arrangement, the less crowded pockets that help separate one group from another, one filament from the next, one local flow from its neighbour. By now, the shape of the cosmic web may be becoming clearer in your mind. Not a smooth universe, not a random scatter, not simply a collection of galaxies floating alone. It is a network of dense knots, stretched filaments, broad walls, large voids, and smaller voids threaded among them. The small voids are part of this network's texture. They matter because they show that emptiness itself has structure at different scales. There are spaces between clusters, spaces between groups, spaces inside larger spaces, and each one carries clues about gravity, dark matter, galaxy formation, and cosmic history. A void-in-void region sounds, at first, like the universe has decided to hide emptiness inside emptiness, the way someone might place a smaller box inside a larger box and then insist this is perfectly normal behaviour. And in a sense, that is almost what is happening. A void-in-void region is a smaller underdense region that sits inside a larger underdense region. It is a pocket of relative emptiness, surrounded not by a crowded, collapsing environment, but by an even wider region that is also emptier than average. This matters because the fate of a small void depends strongly on the larger environment around it. If it lives inside greater emptiness, it has room to grow, spread, connect, and eventually blend into the larger hollow. It is not being squeezed by a busy cosmic neighborhood. It is being carried along by a bigger quietness. That may sound like a small difference, but in the life of a void, it is everything. A small empty region surrounded by dense matter can be compressed, distorted, or erased. But a small empty region inside a large underdense region usually becomes part of the larger void's growth. Matter continues to drain away from it toward the denser walls and filaments beyond. The small hollow expands into the surrounding hollow. Nearby smaller voids may merge. Boundaries that once separated them become less important. The larger low-density region becomes wider, smoother in some places, and more dominant in the map. So a void-in-void process is, very simply, the way small emptiness helps build larger emptiness. The phrase comes from the effort to understand voids as part of a hierarchy. Cosmologists Ravi Sheth and Rien van der Vega describe this idea in models of void evolution, where voids do not simply appear as isolated bubbles. They form, grow, interact, merge, and sometimes vanish depending on their surroundings. This is similar in spirit to the way dark matter halos and galaxy clusters grow hierarchically. Small structures form first, then combine into larger structures. With galaxies and clusters, we often imagine clumps merging into bigger clumps. With voids, the image is stranger but still logical. Smaller low-density regions merge into larger low-density regions. Emptiness grows by joining with emptiness. Imagine a patch of foam again, but this time focus not on the soapy walls, but on the air pockets inside. A few small bubbles might sit close together. If the thin walls between them weaken or shift, those small bubbles can become one larger bubble. The total empty space has not been created from nowhere. It has reorganized. Several little gaps have joined into a bigger gap. Cosmic voids are not soap bubbles, and their walls do not pop in the same tidy way. But the picture helps. In the cosmic web, the boundaries between neighbouring voids can become less meaningful, as matter flows away and the whole underdense region expands. The small voids become subregions inside a larger void, and the larger void becomes the main feature. Of course, the real universe is not a clean cartoon. It has dark matter, gas, galaxies, gravity, expansion, and a long history of uneven growth. A void-in-void region may contain faint galaxies, wisps of matter, weak filaments, and smaller internal patterns. It is not perfectly smooth, but the key point is that both the small void and its larger environment are underdense. They are part of the same general draining of matter away from low-density interiors and towards surrounding denser structures. If you were mapping galaxies, you might first see several neighbouring gaps. With deeper data, you might see faint galaxies between them. With a broader view, you might realise that all those gaps sit inside one larger underdense basin. The classification depends on scale, but the physical idea remains. Emptiness nested inside greater emptiness can grow together. This nesting is one of the reasons voids are such useful examples of cosmic hierarchy. When people hear about hierarchy in the universe, they often think of stars inside galaxies, galaxies inside groups, groups inside clusters, clusters inside superclusters. That is a hierarchy of matter. Voids have their own hierarchy, but it is a hierarchy of low density. Small voids can be embedded in larger ones. Those larger ones can sit within still larger underdense regions. The result is not a set of neat Russian dolls because the shapes are irregular and the boundaries are fuzzy, but the nesting is real enough to matter. The universe builds structure both by gathering matter and by linking the spaces matter leaves behind. The reason this happens goes back to the early universe. The early matter distribution had tiny fluctuations. Some regions were slightly denser than average, and some were slightly less dense. The underdense regions expanded more easily relative to their surroundings because there was less matter inside them to slow their expansion through gravity. Matter tended to move away from their centres toward denser boundaries. Now imagine that within a larger underdense region, there were smaller patches that were even more underdense. Those smaller patches would begin as separate voids, but since the surrounding environment was also low in density, there would not be a strong collapsing pressure to crush them. Instead, the whole region would evolve toward a larger low-density basin. This is why a void-in-void region is often connected to merging. Not merging like galaxies colliding in bright tidal streams, with stars flung outward and gas compressed into new star formation. Void merging is much quieter. It is the fading of the dense ridges or weak boundaries that once separated underdense patches. It is the gradual joining of basins in the matter distribution. A small void expands. Its neighbouring small void expands. The wall between them may become thinner or less distinct compared with the surrounding structure. Over time, they become parts of one larger void. If galaxy mergers are dramatic conversations, void mergers are long pauses becoming one longer pause. This process gives large voids some of their internal structure. A big void may not have started as one simple empty sphere. It may have grown from several smaller voids that joined together. Traces of that history can remain as faint internal filaments, small galaxy chains, or uneven density features inside the larger underdense region. When astronomers study voids in simulations, they can watch this process unfold in a way we cannot watch directly in the sky. The simulated universe begins with tiny density variations, then evolves under gravity and expansion. Voids open, smaller voids connect, and larger void basins form. The final map can look smooth from far away, but if you trace it backward, you see the layered growth. This is useful because it tells us that a large void is not always a simple object. It can be a family history. It can contain the memory of smaller voids inside it. When we map a large void today, we may be seeing the result of many smaller underdense regions joining over billions of years. That makes voids more like evolving landscapes than empty containers. A valley on Earth may be shaped by many streams, landslides, rock layers, and weather over long periods. A cosmic void is shaped by matter flows, gravity, dark matter, and expansion over billions of years. The valley is not just a hole in the ground. The void is not just a hole in space. The void-in-void idea also helps explain why the largest voids tend to dominate the cosmic web's empty volume. As time passes, small voids in underdense regions are absorbed into bigger ones. The larger voids grow, while some smaller boundaries fade. This does not mean every small void disappears from every map. Observational methods can still identify subvoids inside larger regions, especially if faint structures remain. But in a broad physical sense, the emptiness becomes organized into larger basins. The cosmic web becomes more pronounced. Dense regions become denser, and underdense regions become broader and emptier. The contrast increases. You might picture the process as a slow sorting. The universe begins nearly smooth, then gravity sorts matter into denser and less dense places. Denser regions keep pulling in more material. Underdense regions lose material. Inside a large underdense region, the smaller underdensities are sorted into an expanding shared emptiness. It is not chaotic in the everyday sense. It is not random clutter. It is gravity, expansion, and initial conditions working together with deep patience. And patience, as the universe keeps reminding us, is easier when you have billions of years and no urgent emails. There is also an important contrast with the way clumps of matter grow. In the formation of dark matter halos, small halos merge into larger halos, and this process can continue over many scales. The distribution of halo masses has many small objects and fewer large ones. Void evolution is different because small voids can be destroyed, if they form inside overdense regions, a process we will come to next. This creates a more peaked void size distribution in some theoretical models. In simple terms, voids do not behave exactly like matter clumps turned inside out. They have their own rules. Void in void growth builds larger voids, but void and cloud collapse can remove smaller ones. The two processes together shape the population of voids we observe. For the moment, though, we are staying with the gentler case. Void in void regions are the successful growers. They are the small, underdense patches lucky enough to be born in a larger, underdense neighbourhood. They are not fighting against a collapsing crowd. They are part of a widening open region. If a small void could sigh with relief, this would be the one doing it. It has space around it. Its surroundings are also sparse. The matter inside and around it is encouraged, by gravity and the larger density pattern, to move outward toward the denser edges of the whole region. Over time, the small void and its neighbours become less separate and more like features within one growing hollow. This can happen on different scales. A very small underdense patch may become part of a modest void between galaxy groups. Several modest voids may become part of a larger galaxy void. Larger voids may form connected underdense complexes that we might call supervoids, depending on their size and depth. The hierarchy is not perfectly clean, but it is meaningful. It tells us that the empty part of the universe is not static. It is assembling, changing, merging, and responding to the same large-scale forces that shape the bright structures. The galaxies inside void-in-void regions can also tell us something about this growth. Since the environment is underdense on both small and large scales, galaxies inside these regions may be especially isolated. They may have fewer close neighbours, fewer mergers, and less interaction with dense cluster environments. Some may be faint dwarf galaxies. Some may be small gas-rich galaxies forming stars quietly. Their distribution can reveal whether the large void still contains internal filaments, or whether it has become especially sparse. By studying these galaxies, astronomers can learn how galaxy formation proceeds when the surrounding matter field is thin not just locally, but across a larger region. This is one of the reasons void interiors are sometimes described as relatively pristine environments. That does not mean untouched in a perfect sense. Galaxies still form from gas, stars still explode, black holes may still exist, feedback still happens. But compared with cluster environments, void interiors are less disturbed by frequent close encounters and dense surrounding matter. A void-in-void galaxy may be one of the more isolated kinds of galaxy in the cosmic web. It is not outside the universe's story. It is just living in one of the quieter paragraphs. Now, the shape of a void-in-void region can be complicated. If several smaller voids are merging, the larger region may have an irregular outline. Its interior may contain ridges of slightly higher density, remnants of earlier boundaries. Its edges may be defined by galaxy walls and filaments where matter is collected. The whole structure may be stretched by nearby massive regions. So even though the general environment is underdense, the geometry can be lumpy. This matters because void shape is not just appearance. It records gravitational influence. A void that expands in a mostly quiet environment may become rounder over time, while a void near strong external structures may become elongated or distorted. In the cosmic web, shape is history made visible. There's another way to think about void-in-void growth that is especially helpful. Suppose you're looking at a map of valleys and hills. A small dip in the land lies inside a much larger valley. If rain falls, water in the small dip will drain into the larger valley system, and the local depression becomes part of the larger drainage pattern. It is still a feature, but its fate is tied to the larger basin. A void-in-void region works somewhat like that. The small underdense patch is a basin in the density field, and it sits inside a broader basin. Matter flows away from the low-density centre towards surrounding denser ridges. The small basin belongs to the larger one. This is why void-in-void regions are closely connected to the term watershed in some void-finding methods. In a density field, A void can be treated like a basin, and the surrounding denser structures act like ridgelines. Neighbouring basins can merge into larger basins depending on the density ridges between them. These methods are a way of turning the cosmic web into a landscape that algorithms can analyse. The galaxies become markers of density, the voids become basins, the filaments and walls become ridges. It is a very practical way to find structure in a universe that refuses to draw straight borders. In observational maps, though, it can be difficult to decide whether a smaller void is truly a separate void or a sub-void inside a larger region. This is not just a technical nuisance, it is part of the nature of hierarchy. A small void can be real as a local underdensity and also be part of a larger void. Both descriptions can be true at once, depending on the scale of the question. It is similar to saying that a town is real, and a county is real, and a country is real. The town does not stop existing because it is inside a county. The smaller void does not stop being identifiable because it sits inside a larger underdense region. But if you are asking about the larger structure, the larger region may be the more useful description. This layered reality is one reason cosmic void catalogues can differ. One catalogue may list a large void containing several sub-voids. Another may split the same region into many smaller voids. Another may merge them if the density ridge between them is shallow. These differences can sound confusing, but they also show that voids are not simple isolated balls. They are parts of a continuous cosmic density field. We impose categories to study them, but the universe itself is a flowing pattern of density and underdensity. A void-in-void region is one way that pattern reveals its nested nature. The growth of void-in-void regions also connects to cosmic expansion. In an underdense region, there is less matter to slow the local expansion relative to denser areas. So, large voids tend to expand faster than the average matter-filled regions around them, in a relative sense. The centre becomes more underdense while matter piles up around the boundaries. If smaller underdense patches lie within that larger expanding region, they are carried into the same broad expansion. They can stretch, merge, and contribute to the larger void's growth. This does not mean space inside a void is a separate universe. It simply means that the local density environment affects how structures evolve within the expanding universe. Dark energy adds another layer to the story. As the universe's expansion accelerates, the growth of structure changes. Dense regions remain gravitationally bound where they are strong enough, but on very large scales the expansion increasingly dominates. Voids are especially useful for studying this because their evolution is sensitive to the balance between gravity and expansion. A void-in-void region, expanding within a larger underdensity, can act as part of this test. Its size, shape, and density profile can help cosmologists compare observations with models of cosmic acceleration. So again, emptiness becomes a measuring tool. The phrase empty spaces growing inside greater emptiness may sound almost too quiet for something scientifically powerful, but it captures an important truth. The universe does not only evolve by making things, it evolves by making room between things. Voids grow as matter leaves. Larger voids grow as smaller voids merge. The open spaces become more open, while the crowded strands become more crowded. This is not a side effect. It is the cosmic web becoming itself. There is something restful about imagining that process, not because it is small or simple, but because it is slow and clear. Matter moves toward gravity. Low-density regions widen. Boundaries shift. Small voids join into larger ones. No sudden explosion is needed. No central engine. No dramatic blast wave sweeping galaxies aside. Just the deep logic of structure formation unfolding across enormous distances and times. The universe rearranges itself, and emptiness takes shape. If you were to drift through a void-in-void region in thought, you might not notice the nesting at first. From inside, everything would simply feel sparse. Galaxies would be far apart. large clusters would be distant. The sky beyond any local galaxy would reveal fewer nearby bright systems, but if you could rise far enough above the map, you would see the hierarchy. The small hollow you crossed would sit inside a larger hollow. That larger hollow might connect to others. Its edge would be outlined by walls and filaments. The empty region would no longer seem like a blank. It would look like a basin within a basin, a quiet place being gathered into a wider quiet. A void in cloud region is where the story of cosmic emptiness becomes a little less peaceful. So far, we have mostly followed the kind of emptiness that has room to grow. We have watched small voids sit inside larger underdense regions, merge with their neighbours, and become part of a wider quiet. That is the gentler path, the void in void path, where emptiness expands into more emptiness. But not every small void is born into such friendly surroundings. Some begin as little underdense pockets inside a larger region that is, overall, denser than average. Around them, matter is not drifting away into a wide cosmic hollow. It is gathering, collapsing, and pulling inward. The small void may be real for a while, but it is surrounded by a cosmic crowd, and that crowd can squeeze it until the underdensity shrinks, distorts, or disappears. That is the basic idea of a void in cloud region. It is a small void embedded within a larger overdense environment. The word cloud here does not mean a cloud of gas like a nebula, and it does not mean something soft and white drifting across a summer sky. In this context, cloud means an overdense region, a larger patch of the universe where matter is more crowded than average and is moving toward collapse or strong structure formation. It may be a region that will become part of a wall, a filament, a group, or a cluster. Inside that larger crowded environment, a small underdense pocket may appear, but its future is very different from the future of a void surrounded by emptiness. It is like a quiet corner in a room slowly filling with people. The corner is quiet for now, but the room has plans. This idea was developed as part of the hierarchical view of cosmic voids. In that view, voids do not simply form once and stay fixed forever. They evolve through two broad processes. One is void in void, where smaller voids in larger underdense regions merge and help build larger voids. The other is void in cloud, where smaller voids inside larger overdense regions are squeezed out as the surrounding overdensity collapses. This second process is special because it gives voids a kind of lower size limit. Tiny voids are not always allowed to survive. Many of them are erased by the larger structures around them before they can become long-lived features of the cosmic web. At first, that may feel strange. We're used to thinking of dense objects as things that can be crushed. A star can collapse, a gas cloud can fall inward, a dark matter halo can grow denser, but how can emptiness be crushed? The answer is that a void is not a solid object. It is a region of lower density. To crush it means to change the motion and density of matter around it so that the low density contrast is reduced or erased. The surrounding matter falls inward. Filaments and walls press closer. Galaxies and dark matter move in ways that make the empty pockets smaller. The void's boundary shifts. Its shape stretches, flattens, or collapses along one or more directions. The emptiness does not break like glass. It fades as the surrounding density field overwhelms it. Imagine a small bubble inside thick dough as the dough is kneaded. If the dough expands around it evenly, the bubble might grow or join with other bubbles. But if the dough is pressed from all sides, the bubble can shrink and vanish. This is not a perfect comparison, because cosmic voids are not air bubbles, and the universe is not making bread, although after enough cosmology, fresh bread does sound very comforting. Still, the image helps. A void in cloud region is a small hollow inside material that is being pressed, gathered, or collapsed by gravity. The hollow may not survive the larger motion. The reason this happens is rooted in the same early density fluctuations that made all cosmic structure. In the young universe, some patches were slightly denser than average, and some were slightly less dense. A small patch might be underdense, but if it sits inside a much larger region that is overdense, the larger region's gravity can dominate the smaller patch's future. On its own, the small underdensity might expand, but it is not on its own. It lives inside a bigger environment whose gravity is pulling matter together. That larger collapse can overpower the local expansion of the little void. So the small void is caught between its own tendency to become emptier and its surroundings' tendency to become more crowded. In a void in cloud case, the surroundings win. This is one of the useful lessons voids teach us. You cannot understand a structure only by looking at its own density. You must also ask where it lives. The same small underdense patch may have two different fates, depending on whether it is embedded in a larger void or a larger overdense region. In a larger void, it may grow. In a larger cloud, it may collapse. The small-scale feature is real, but the large-scale environment decides the long-term story. The universe is not just a collection of isolated parts. It is a nested, interacting pattern. That nested pattern is what makes the cosmic web so rich. A small void near the boundary of a large void may be pulled and stretched by nearby filaments. A small underdensity inside a future wall may be flattened as the wall forms. A little gap between forming galaxy groups may be squeezed as the groups draw in matter. In some directions the void may still expand, in others it may contract. This is called anisotropic evolution, which simply means the behaviour is not the same in every direction. A void does not have to collapse like a balloon shrinking evenly. It may be compressed along one axis while stretching along another. The result can be a strange flattened or elongated underdense region, a void that is not simply growing or dying, but being reshaped by the surrounding cosmic crowd. This is especially common near walls and filaments. The edges of large voids are not calm borders. They are active regions where matter collects. Galaxies line up, dark matter gathers, gas flows, smaller structures form. These boundaries can be busy, gravitationally speaking. A small void near such a boundary may be affected strongly by nearby overdense structures. It might appear as a little underdense pocket in a galaxy map, but the surrounding mass distribution may be pulling it apart or squeezing it inward. If you could watch the cosmic web evolve over billions of years, some of these small voids would not simply sit there. They would be stretched, flattened, and absorbed into the growing walls and filaments. This is why void in cloud regions can be less intuitive than large expanding voids. When we picture a void, we often imagine a round, empty bubble expanding outward. But many underdense regions are not like that. Some are caught in larger flows. Some expand along one or two directions but contract along another. Some are small, temporary depressions in a landscape that is overall moving toward collapse. Their identity as voids may depend on the moment in cosmic time and the way we identify them. A region can be underdense now, but not destined to remain a stable void forever. There is a bedtime sort of humility in that thought. Even emptiness can be temporary, not because the universe is impatient, but because gravity keeps rearranging the pattern. A small quiet region can be swallowed by a larger structure. A faint gap can vanish as matter gathers around it. The cosmic web is not a frozen sculpture. It is an evolving system, even if the changes take far longer than any human life, civilization or species has yet managed to sit through with a notebook. Scientists describe this in theoretical models using something called the two-barrier problem. We do not need to climb too far into the mathematics, but the idea is helpful. When modelling the formation of dark matter halos, researchers often ask when a region becomes dense enough to collapse into a bound object. That involves one threshold or barrier. With voids, there are two important possibilities. A region may become underdense enough to form a void, but it may also sit inside a larger overdense region that collapses. So one barrier describes void formation, and the other describes the surrounding collapse that can destroy small voids. The void and cloud process is what makes that second barrier necessary. It is the universe saying, yes, this small region is empty, but please check the neighbourhood before making long-term plans. The effect of this process is that very small voids may be rare among long-lived mature voids. Many of the smallest underdense pockets are squeezed out of existence by their larger environments. This helps explain why void-size distributions can have a characteristic scale, rather than continuing endlessly toward tiny voids, in the same way some clump populations can extend towards smaller masses. In simpler words, the universe does not preserve every little empty gap. The crowded parts erase some of them. The void population we observe is shaped not only by the creation of emptiness, but by the destruction of emptiness too. This may seem like a strange thing to say, the destruction of emptiness, but it is a useful phrase if we understand it properly. What is destroyed is not space itself. Space remains. What disappears is the underdense identity of the region. The density contrast changes. The low-density pocket is filled in or compressed relative to its surroundings. The small void stops being a recognizable void in the matter distribution. It becomes part of a wall, filament, or collapsed structure. The room does not vanish from the universe. The room fills with furniture. Observationally, void and cloud regions can be difficult to identify. A galaxy survey may show a small region with fewer galaxies, but whether that region is expanding or contracting depends on the mass distribution and motions around it. Galaxy counts alone may not tell the full story. Astronomers need to consider the environment, nearby structures, velocity flows, and sometimes reconstructions of the dark matter distribution. A small void near dense walls may be very different dynamically from a small void deep inside a larger underdense basin, even if their galaxy counts look similar at first glance. This is why void classification is not just about size, it is about context. In nearby void studies, researchers sometimes find that underdense regions identified through galaxy distributions do not always match a simple picture of freely expanding empty basins. Some appear to be influenced strongly by nearby overdense filaments and walls. They may be contracting in one or more directions. Their flow fields can be dominated by tidal forces from the surrounding cosmic web. Tidal forces are differences in gravity across a region, the same general idea that lets the moon raise tides on Earth. Though here we are talking about the vast gravitational pattern of galaxy structures. These tidal influences can stretch or squeeze a void, changing its shape and future. The void is not just empty, it is being handled very slowly by the gravity around it. A good mental image is a small depression in a thick sheet as the sheet is being folded. The depression may exist, but if the sheet is folded toward it, the depression becomes squeezed and distorted. The larger motion dominates. In a void in cloud region, the large-scale overdensity acts like that folding sheet. Matter is moving inward as part of a broader collapse or compression. The small void is caught inside that movement. It may survive for a while as a recognizable underdensity, but it is not the kind of void that grows calmly into the far future. There are also observational complications because galaxies are only traces of the underlying mass. A small region may have few bright galaxies, but nearby dark matter structures may still exert strong gravity. The void may look empty in visible light, while being dynamically influenced by invisible mass around it. That is one reason dark matter matters so much for void studies, and it is one of the reasons we will soon move from galaxy-defined voids toward dark matter voids. The visible map is beautiful, but incomplete. A void in cloud region especially reminds us that what we see may not fully reveal what the mass is doing. This is important for galaxy evolution too. A galaxy inside or near a void in cloud region may not experience the same calm isolation as a galaxy deep inside a large expanding void. If the small void is near walls, filaments, or forming groups, the environment may be more active. Nearby structures can influence gas flows, galaxy motions, and interactions. The region may be underdense compared with a cluster, but it is not necessarily peaceful on every scale. It may be a transitional environment, partway between void interior and denser web. Galaxies there can help astronomers study how environment changes gradually from sparse regions to crowded ones. The boundary between a void and a filament is not merely a line. It is a zone where cosmic conditions change. In the center of a large void, galaxies may be isolated and faint. Near the edge, galaxies become more common and may align along walls. In a void in cloud setting, the small underdensity may live so close to dense surroundings that its galaxies are influenced by those structures. This makes the environment more complicated, but also more informative. It is in these messy transitions that the cosmic web reveals how matter moves from empty basins into crowded highways. There is a simple question that helps separate the two paths. Is the larger environment expanding away from the void or collapsing around it? In a void-in-void region, the small underdensity belongs to a bigger low-density area. The larger environment supports its growth. In a void-in-cloud region, the small underdensity belongs to a bigger high-density area. The larger environment works against it. It is the same small quiet patch, but one is in a quiet countryside, and the other is in the middle of a city being built around it. The future is not the same. This idea also reminds us why maps of the universe must be read at multiple scales. If you zoom in too closely, you may see a small void and think it is an independent feature. If you zoom out, you may realize it sits inside a larger overdense region and is likely to be crushed. If you zoom out in a different case, you may find that another small void sits inside a larger underdense basin and will probably merge into a bigger void. The truth depends on the zoom level. Cosmology is full of this. A galaxy is huge, but it is a particle in a large-scale map. A cluster is enormous, but it is a knot in a web. A void can be large, yet still be a sub-void inside something larger. Scale is not just measurement. Scale is meaning. For a sleepy mind, perhaps the best way to imagine void-in-cloud regions is as small pockets of quiet being overtaken by the growth of cosmic structure. Not violently, not quickly, but inevitably if the surrounding environment is dense enough. Gravity gathers matter into walls and filaments. Those structures press inward. The little void contracts along certain directions. Its boundaries blur. Its identity fades. What was once a low-density pocket becomes part of the crowded architecture. The universe does not mourn it, of course. The universe is not sentimental about underdensities, but we can notice the process and feel a small, curious sympathy for the little hollow that did not get enough room to become a grand void. And this contrast makes the surviving large voids more interesting. They are not simply the result of underdensities forming. They are the result of underdensities forming in the right environments. The voids that grow large are those not erased by surrounding collapse. The voids that remain visible in the cosmic web are the winners of a long environmental sorting process. Some were absorbed into greater emptiness. Some were squeezed by cosmic crowds. The population we see is shaped by both growth and loss. This also helps explain why voids are powerful cosmological probes. Their sizes, abundance, shapes, and internal motions depend on gravity, dark matter, dark energy, and the initial conditions of the universe. If gravity were different, the balance between expansion and collapse might change. If dark matter behaved differently, small structures and small voids might form differently. If dark energy influenced expansion in another way, large voids might grow at different rates. The little void and cloud regions, even the ones that do not survive, are part of that larger record. They help determine the final pattern. There is a kind of quiet drama here, but it is not the drama of explosions or cosmic monsters. It is the drama of environment. A small void tries to become emptier. Its surroundings decide whether it succeeds. The crowded cloud collapses around it, and the small void is squeezed. The open underdense region expands around it, and the small void grows. Two fates, both born from the same basic physics, separated by where the void happens to be. The universe, once again, turns out to be very interested in context. When we look at a map of cosmic voids made from galaxies, it is tempting to think we're seeing the universe as it truly is. Galaxies shine. They gather in clusters. They stretch along filaments. They outline walls, knots, and the great open spaces between them. So when a region has very few galaxies, we call it a void, and that seems sensible enough. But galaxies are only the visible lanterns hanging on a much larger invisible frame. They do not make up most of the matter in the universe. They do not trace every hidden curve of gravity. They are bright clues, not the whole answer. Behind every visible void, behind every galaxy pore hollow in the cosmic web, there is a deeper question waiting quietly in the dark. Is the invisible matter missing there too? That question takes us into dark matter voids, the hidden hollows behind the visible ones. A dark matter void is a region where the density of dark matter is lower than average. It may correspond closely to a galaxy void, because galaxies usually form within dark matter halos, and where there are fewer halos, there are usually fewer galaxies. But the relationship is not perfect. A galaxy map is like looking at a city at night from far above. The lights tell you where many people are, but not every person has a light on, and not every road is visible from the sky. Dark matter is the unseen ground plan beneath those lights. It shapes where galaxies can form, where they gather, how they move, and how the web itself holds together. Dark matter is called dark, not because it is spooky, although it has certainly earned a suspicious little glance from physicists, but because it does not emit, absorb, or reflect light in the way ordinary matter does. We cannot see it directly with telescopes. We infer it from gravity. Galaxies rotate as if there is more mass present than we can see. Galaxy clusters hold together and bend light as if much more matter exists than stars and gas can explain. The large-scale cosmic web grows in a way that requires invisible mass helping gravity build structure. Dark matter does not shine, but it leaves fingerprints everywhere. It is like the quiet person in the room who rearranged all the furniture while insisting they were not doing anything. So when astronomers map voids using galaxies, they're using the visible part of the story to trace the invisible part. Most of the time this works reasonably well. Galaxies form in dense enough dark matter halos, and halos form in the underlying dark matter field. If a region has very few galaxies, it is usually also underdense in dark matter, but usually is doing some work here. Galaxies are biased tracers of matter, which means they do not follow the dark matter distribution perfectly. They prefer certain environments. Bright galaxies tend to form in more massive halos. Faint galaxies can live in smaller halos. Some dark matter halos may contain little or no visible galaxy. Some galaxies may be too faint for our surveys to detect, so a galaxy void and a dark matter void are connected, but they are not always identical twins, perhaps cousins, quiet cousins, living several million light-years apart. This difference matters because the true gravitational shape of a void depends on the total matter, not just the visible galaxies. A region could look extremely empty if we count only bright galaxies, but it might still contain a population of faint galaxies or dark matter halos below our detection limits. Another region might be genuinely underdense in both visible and dark matter. These are not the same situation. If we want to use voids to test cosmology, gravity, dark energy, or the nature of dark matter itself, we need to know the deeper matter distribution. The visible hollow is useful, but the invisible hollow is the real gravitational basin. Computer simulations are one of the main ways scientists study this. In a simulation, researchers can follow dark matter directly, because inside the model universe every particle is known. They can create a cosmic web, identify voids in the dark matter distribution, and then compare those voids with the voids that would be found if they only looked at simulated galaxies or halos. This is very helpful, because in the real universe we do not get to press a button marked Show Dark Matter, which is a shame because many astronomers would use it immediately and probably forget to eat lunch. These simulations show that galaxy voids often do correspond to real underdensities in the dark matter field, especially when the galaxy survey is dense enough. That is reassuring. It means galaxy voids are not just illusions created by missing visible objects. They really do tend to mark places where the underlying matter density is low, but simulations also show differences. Galaxy-defined voids can have slightly different sizes, centers, and density profiles compared with voids defined directly in dark matter. In some work, galaxy voids trace the same broad underdense regions as dark matter voids, but can appear larger and shallower, with centers offset from the true dark matter underdensity. In simpler terms, galaxies can point us toward the hidden hollow, but they may not put the pin exactly in the center. This is easy to understand if we remember that galaxies are discrete objects. Dark matter forms a smoother field in simulations, while galaxies are scattered points. If you're trying to find the center of a quiet region, using only a handful of visible markers around it, your estimate may be a little off. It is like trying to find the quietest spot in a park at night by looking only at the few lamps along the paths. You can make a good guess, but the darkness itself has a smoother shape than the lamp map reveals. Dark matter voids help correct that picture. There is another way to study the invisible hollow, and it is one of the cleverest tools in astronomy: gravitational lensing. Gravity bends light. When light from distant galaxies travels through the universe, its path is slightly distorted by the matter it passes along the way. Dense regions, such as galaxy clusters, bend light more strongly and can create dramatic lensing effects, even arcs and multiple images in extreme cases. Voids do the opposite in a subtle way. Because they contain less matter than average, they produce a weak lensing signal associated with a mass deficit. They do not bend light like massive clusters. They create a quieter, opposite kind of distortion, a faint signature of missing mass. This is not something you can see by looking at one background galaxy. The effect is too small. Astronomers need to stack many voids together, comparing the tiny shape distortions of many background galaxies behind many underdense regions. When the signal builds up statistically, it can reveal the matter profile of voids. In other words, weak lensing lets scientists weigh the emptiness. That phrase sounds odd, weighing emptiness, but it is exactly the kind of odd phrase cosmology gives us with a straight face. By measuring how much lensing is missing compared with the average regions, astronomers can infer how underdense the void really is in total matter. This is where dark matter voids become more than an invisible idea. They become measurable. Surveys such as the Dark Energy Survey have used weak gravitational lensing to study voids and confirm that galaxy-identified voids are also underdense in dark matter. More recent lensing work has continued pushing this method forward, measuring stacked void density profiles and comparing the matter distribution with the galaxy distribution. These measurements are difficult because the signal is weak and the universe is noisy, but they are powerful. They allow astronomers to test whether light and mass tell the same story in the emptiest regions. The shape of a dark matter void can be described by its density profile. Near the center, the matter density is low. Moving outward, the density rises. Around the edge, there may be a ridge where matter is piled up into walls and filaments. This profile is important because different kinds of voids can have different profiles. Large voids in underdense environments may have deep centers and gentle edges. Smaller voids inside overdense regions may have dense surrounding ridges and more complicated profiles. The dark matter profile reveals whether the void is growing freely, being squeezed, or sitting in a transitional environment. It is like reading the pressure marks around a footprint, except the footprint is hundreds of millions of light years wide and made of missing matter. dark matter voids also help explain why the cosmic web has the structure it does. Dark matter begins the process. In the early universe, ordinary matter and radiation were tightly connected, but dark matter could start clumping under gravity earlier in a different way. It formed the gravitational scaffolding into which ordinary matter later fell. Galaxies formed inside dark matter halos, and those halos gathered along filaments and clusters. Voids opened where the dark matter density was low, so the visible cosmic web is, in a sense, a lit-up version of a darker web beneath it. The galaxies are stars on the stage, but dark matter built much of the stage. This does not mean dark matter is spread only in filaments and absent from voids. Even voids contain dark matter. They are underdense, not empty. A dark matter void still has some dark matter inside it, just less than the cosmic average. That lower density is what matters. It changes the local gravitational environment, the growth of galaxies, the motion of matter, and the lensing signal. The void is not defined by zero. It is defined by contrast. Contrast is one of the most important ideas in this entire subject. A galaxy cluster is meaningful because it is denser than average. A void is meaningful because it is less dense than average. The cosmic web is a pattern of contrast, not a pattern of absolute presence and absence. Dark matter voids are the contrast beneath the contrast. They show that the visible gaps between galaxies are rooted in the deeper mass distribution of the universe. This is also why dark matter voids are useful for testing the nature of dark matter itself. Different dark matter models can produce different small-scale structures and different void properties. Cold dark matter, the standard picture, allows structure to form in a certain way, with many small halos and a particular web of density and underdensity. Warm dark matter or other more exotic possibilities can smooth small-scale structure differently. If dark matter is more diffuse, or if it behaves in ways beyond the simplest model, void density profiles and the abundance of small voids may change. The emptiest places become a way to ask what the invisible substance is like. That may sound counterintuitive. If you want to understand dark matter, why look where there is less of it? But low-density regions can be especially revealing. In dense regions, many complicated processes overlap. Galaxies form stars, black holes inject energy, gas heats and cools, mergers stir matter, and ordinary physics can make the picture messy. In voids, there is less baryonic matter, fewer galaxies, and less astrophysical clutter. This makes them sensitive to the underlying rules. If gravity or dark matter behaves slightly differently from what we expect, voids may show that difference more clearly than crowded clusters do. The quiet room lets you hear the clock. Modified gravity theories are also tested with voids. In Einstein's general relativity, gravity behaves in a particular way, and the standard cosmological model uses that behavior to predict the growth of structure. Some alternative theories propose small changes to gravity on cosmic scales. Many such theories include screening mechanisms which hide deviations from general relativity in dense environments like galaxies and clusters. But voids are low-density environments, so screening may be weaker there. That means any modified gravity effects could become more noticeable in voids. If the universe is trying to whisper that gravity has extra behavior, voids may be one of the better places to listen. Weak lensing is especially useful for this because lensing measures the gravitational effect of matter directly, regardless of whether that matter shines. If a modified gravity model predicts a different relationship between matter, light bending, and structure growth, void lensing can help test it. The signal is not easy. It requires large surveys, careful statistics, and precise control of errors. But the principle is elegant. Look at the places with missing mass, measure how light responds to that missing mass, and compare the result with what our theories predict. Dark energy also enters the story. Dark energy is associated with the accelerated expansion of the universe, and voids are sensitive to expansion because they are underdense. In dense regions, gravity can bind matter together and resist expansion locally. In voids, there is less matter to resist the expansion, so voids tend to grow relative to denser regions. The sizes, shapes, and profiles of dark matter voids may therefore carry information about cosmic acceleration. This does not mean a single void can reveal dark energy on its own, but a large population of voids, carefully measured, can become part of the larger cosmological toolkit. Neutrinos may also leave signatures in voids. Neutrinos are extremely light particles that move very fast and affect the growth of structure in subtle ways. Because voids are sensitive to diffuse components and the overall growth of matter clustering, they may help constrain the total mass of neutrinos when combined with other measurements. So a dark matter void is not only a hollow in the invisible mass field, it is a meeting point for several deep questions. What is dark matter? How does gravity work? What is dark energy doing? And how do light particles influence the growth of the cosmic web? That is quite a lot of responsibility for something called a void. It is like asking the quietest person at the dinner table to explain the entire family history. And yet, sometimes the quietest person has been noticing everything. To make this more concrete, imagine two maps of the same region of the universe. The first is a galaxy map. It shows bright points where galaxies are detected. In one large region, the points thin out and astronomers identify a void. The second is a dark matter map, built from simulations or inferred through weak lensing. It shows the smoother mass distribution beneath the galaxy points. In that second map, the same region appears as a broad, low-density basin. The galaxy void and the dark matter void overlap, but not perfectly. The centre may shift slightly. The edge may look smoother. The dark matter profile may reveal a surrounding ridge that the galaxy map only hints at. Both maps are true in their own way. Together they are better than either alone. This relationship between galaxies and dark matter is called bias. Galaxies are biased tracers because they do not form everywhere with equal efficiency. Inside voids, galaxy bias can vary with distance from the void centre, void size and environment. Galaxies near void edges may trace denser surroundings differently from galaxies deep inside. Some voids surrounded by over-dense regions have different tracer behaviour than large expanding voids surrounded by underdense environments. This sounds technical, but the basic idea is simple. The lights do not perfectly trace the land. To understand the land, we must learn how the lights are placed. Dark matter voids are also connected to the motions of galaxies. In and around a void, matter tends to flow outward from the underdense interior toward the denser walls and filaments. Galaxies near the edges can have motions that reveal the void's gravitational influence. Redshift space distortions, which are apparent distortions in galaxy maps caused by galaxy motions along our line of sight, can help measure these flows. The pattern of motion around voids can test gravity and expansion. Again, the void is not doing nothing. Its low density affects how matter moves around it. If you could see dark matter directly, the universe would look very different. The bright galaxies would no longer be isolated islands. They would sit inside halos. Those halos would connect to larger filaments. Clusters would become immense dark knots. Voids would become enormous dim basins, not black empty holes, but smoother regions where the invisible matter thins out. You would see that the visible universe is only the sparkling surface of a deeper gravitational ocean. Some places would be bright with stars, but also heavy with unseen mass. Other places would be dim in both light and mass. Dark matter voids would be the broad shallows in that ocean, places where the gravitational water is drained toward the surrounding currents. This image also helps us avoid a mistake. A void is not empty because something pushed matter away with a force from the centre. It is empty because structure formation drew matter elsewhere. Dark matter flowed toward denser regions under gravity, leaving underdense basins behind. Ordinary matter and galaxies followed the deeper dark matter framework. The visible void is a consequence of the invisible void. If the dark matter field had been different, the galaxy web would have been different too. That is why dark matter voids sit behind all the earlier types we have discussed. Ordinary galaxy voids are visible traces of matter scarcity. Supervoids are enormous low-density regions in both galaxy and matter distributions. Mini-voids are smaller underdense pockets that may be revealed or hidden depending on the tracers used. Void in void and void in cloud regions depend on the surrounding density field, which is fundamentally shaped by dark matter. Dark matter voids are not just another category sitting beside the others, they are the deeper layer beneath them. Still, astronomers must be cautious. Dark matter is inferred, not photographed directly. Simulations depend on assumptions. Lensing signals are small. Galaxy surveys have limits. Void finding methods differ. The invisible hollow is real in the sense that gravity reveals it, but measuring it precisely is difficult. That difficulty is part of why void science is growing. New surveys can map more galaxies, measure better redshifts, detect weaker lensing signals, and compare observations with increasingly detailed simulations. The more data we gather, the sharper the dark matter voids become. There is a lovely reversal here. For a long time, voids were treated as the empty spaces between the important things. Now they are becoming important because they are empty. Their low density makes them clean laboratories. Their invisible mass deficits can be measured through lensing. Their shapes and motions can test gravity. Their galaxy populations can test how visible matter traces dark matter. Their abundance can test cosmological models. The void, once a blank area on the map, becomes a quiet instrument. And perhaps that is the best way to think of a dark matter void tonight. Not as nothing, not as a hole, not as an absence without purpose, but as an invisible hollow in the universe's gravitational structure. Galaxies show us where the hollow may be. Weak lensing helps weigh it. Simulations help explain how it formed. Its profile tells us how matter drained away and gathered along the edges. Its shape tells us about surrounding forces. Its population of faint galaxies, if any, tells us how ordinary matter behaves when the dark scaffolding is thin. As we drift through this hidden layer of the cosmic web, the universe becomes a little stranger and a little clearer at the same time. The bright map of galaxies is beautiful, but it is not the whole map. Behind it lies the dark matter field, and within that field are hollows that may be larger, smoother and deeper than the visible galaxies alone suggest. Every galaxy void is, in some sense, a doorway into this invisible structure. Every empty-looking region asks us to look beyond light and follow gravity instead. Now that we have followed voids from visible galaxy maps down into the invisible dark matter scaffolding beneath them, it is time to bring the emptiness a little closer to home. Not close in the human sense, of course. A nearby cosmic void is still so large and distant that calling it local feels like a joke told by someone who measures their errands in light years. But in cosmology, local simply means part of our broad neighbourhood, the region of the universe around the Milky Way, where galaxy distances and motions can be mapped in useful detail. And in that neighbourhood, we do not find a smooth, even spread of galaxies. We find clusters, groups, filaments, sheets, and great empty regions with names. Some are famous, some are debated, some sit near us quietly, shaping the motion of galaxies without ever glowing, exploding, or doing anything dramatic enough to get its own action film. One of the most important nearby examples is the local void. The name is plain, almost modest, but the object itself is anything but small. The local void is a large underdense region adjacent to the local group, the small galaxy family that includes the Milky Way, Andromeda, Triangulum, and many dwarf galaxies. It is not a perfectly empty bubble. It is not a clean round hole. It is a real underdense region, complex and partly hidden from our view, because part of it lies behind the dusty plain of the Milky Way. That is one reason it has taken careful work to understand. Our own galaxy, beautiful as it is, can be a nuisance when you're trying to look through it. It is like trying to study the landscape outside, while standing behind a very bright, very starry curtain. The local void matters because it is part of our address. We are not simply floating in an average place in space. The Milky Way sits near the edge of a relatively flat arrangement of nearby galaxies, often called the local sheet, and beside that sheet lies the local void. On other sides are denser structures, including the Virgo cluster region and larger filaments. This means our neighbourhood has a strong contrast: matter gathered in one direction, emptiness in another. The result is not only a map of where galaxies sit, it is also a map of how they move. Galaxies are not perfectly fixed points in the expanding universe. On very large scales, space expands and galaxies move away from one another with the Hubble flow. But on top of that smooth expansion, galaxies also have peculiar velocities, which are extra motions caused by gravity from nearby structures. Dense regions pull, underdense regions shape motion by lacking that pull and by expanding relative to their surroundings. The local void is thought to have a significant dynamical effect on our region. Studies using galaxy distances and motions suggest that the local group has a motion component away from the local void, while also being pulled toward denser regions such as the Virgo cluster. So even emptiness, by having less gravity than its surroundings, helps shape our cosmic motion. That may sound strange at first. How can nothing push? Strictly speaking, the void is not pushing in the way a hand pushes a door. What happens is that gravity is uneven. Matter on the denser side pulls more strongly than matter on the emptier side. The underdense region also expands more freely relative to denser structures. The combined effect looks like motion away from the void. It is not a mysterious repulsive force from nothingness. It is the ordinary result of gravity in an uneven universe. Still, the image is hard to resist. The crowded places tug us in, and the empty places make the tug from that direction weaker. Our galaxy moves through a cosmic landscape shaped by both presence and absence. The local void is also not alone. Modern maps suggest that voids form an interconnected network, just as galaxy filaments do. The local void appears connected through passages to other large nearby void regions, including the Hercules and sculptor voids. This is a lovely reversal of the usual cosmic web picture. We often imagine filaments as the connected parts and voids as the spaces between them. But voids themselves can also connect, forming channels and basins of underdensity. The bright web has an inverted partner, a dark open web of hollows and passages. If the galaxies are the roads, the voids are the broad open lands between roads, and some of those open lands join together into larger regions. The sculptor void, for example, is part of the wider nearby underdense geography. It lies in the direction of the sculptor constellation and is often mentioned in studies of the local cosmic web. The Hercules void is another named underdense region connected to larger nearby structures. These names can feel like labels placed on a map, and in a way they are, but they help astronomers talk about real features in the galaxy distribution. Just as we name seas, mountain ranges, and deserts on Earth, cosmologists name large underdense regions so they can describe the universe's geography with more than coordinates and numbers. Of course, coordinates and numbers still do most of the work. The names are simply friendlier at bedtime. The Buta's void is one of the most famous named voids, and it deserves its reputation. It lies in the direction of the constellation Buta's and is often nicknamed the Great Nothing. Discovered through redshift surveys in the early 1980s and confirmed with follow-up work, it stood out because a very large region contained far fewer galaxies than astronomers expected. Later observations did find galaxies inside it, including gas-rich systems, so the name Great Nothing is not literally correct. It is more like the Great Not Very Much, which is scientifically better, but admittedly less catchy. Still, the Buta's void remains a classic example of how absence became visible once astronomers could map galaxy distances in 3 dimensions. There is an important lesson in the Buta's void. A void can be famous because it looks empty, and then become even more interesting when it turns out not to be completely empty. the galaxies inside it are not failures of the void definition. They are part of the void environment. They show that voids can host galaxies, but at a much lower density than average. They also give astronomers a chance to study how galaxies evolve in very sparse surroundings. A galaxy inside a famous void becomes a kind of test subject for isolation. It asks what happens when a galaxy grows far from the busiest filaments and clusters. Does it form stars differently? Does it keep its gas longer? Does it have fewer mergers? The void is not just the empty region around the galaxy. It is part of that galaxy's life story. The Eridanus supervoid is another named structure, and it carries a different kind of interest. It lies in the direction of the constellation Eridanus, and has been studied because of its possible connection with the cold spot in the cosmic microwave background. The cosmic microwave background is the afterglow of the early universe, and the cold spot is a region that appears cooler than expected over a large area of the sky. One idea is that a large underdense region along the line of sight, such as the Eridanus supervoid, could contribute to that cold appearance through the integrated Sachs-Wolf effect, where light loses or gains tiny amounts of energy while crossing large evolving gravitational structures. But this is not a simple solved case. Recent studies have confirmed a significant underdensity in that direction, yet they also suggest that the supervoid may explain only part of the observed temperature depression if the standard cosmological model is assumed. So Eridanus is not just a named void. It is a named argument, a place where observations, theory and uncertainty meet. That is often how named voids work. They are not just landmarks, they are questions. The Botas void asks how large and empty a galaxy-poor region can be. The local void asks how emptiness influences the motion of our own neighbourhood. The Eridanus supervoid asks whether a large underdensity can help explain an unusual feature in the ancient light of the universe. The KBC void asks whether we might live inside a much larger local underdensity that could affect measurements of cosmic expansion. Each named void carries a slightly different scientific personality, which is a polite way of saying that each one causes its own set of headaches for astronomers. The KBC void, named after Ryan Keenan, Amy Barger, and Lennox Cowie, is especially interesting because it concerns the possibility that our wider local universe is underdense on scales of several hundred megaparsecs. The idea comes from studies of galaxy counts and luminosity density, particularly in the near-infrared, suggesting that the local region may contain less matter than the cosmic average. If true, that could influence local measurements of the expansion rate of the universe, because galaxies flowing out of an underdense region may make the local expansion appear slightly faster. This is why the KBC void often appears in discussions of the Hubble tension, the disagreement between expansion rates measured from the nearby universe and those inferred from the early universe. But this is a debated topic, and it should be treated carefully. A local underdensity may exist, but how large it is, how deep it is, and whether it can explain much of the Hubble tension are all active questions. Some studies suggest it might reduce part of the tension. Others find that it cannot solve the full problem, or that the required void would be difficult to fit within the standard cosmological model. The KBC void is therefore not a settled answer. It is a proposed feature, a possibility under investigation, and a reminder that even our own cosmic neighbourhood is not fully understood. The universe, rather inconveniently, did not place us in a perfectly average test chamber with clear labels on every wall. This brings up a subtle issue. When we talk about living in a void, we have to be precise about scale. The Milky Way is not inside the empty centre of the local void. We are near its edge. The solar system is inside a galaxy surrounded by stars, gas, dust, planets, and a very enthusiastic number of small icy objects. The Milky Way is inside the local group, which is not empty. The local group sits within a broader sheet and near larger structures. So if we say we are near or perhaps within a larger local underdensity, that does not mean the night sky should look blank, or that our galaxy is lonely in an absolute sense. It means that compared with the cosmic average over large enough scales, the matter density around us may be lower than average. Cosmic language often uses familiar words in unfamiliar ways. Local does not mean next door. Empty does not mean nothing. Inside does not always mean in the middle. This is how astronomy keeps everyone humble. Named voids are also affected by the way we observe the sky. Some regions are easier to map than others. The Milky Way blocks part of our view with stars, dust and gas in what astronomers call the zone of avoidance. It is a wonderfully dramatic name for the region, where our own galaxy makes distant extragalactic observations difficult. The local void lies partly behind this zone, which makes its structure harder to map. To study such regions, astronomers use infrared surveys, radio observations of neutral hydrogen, galaxy motions, and reconstructed density fields. They are not simply taking a photograph of emptiness. They are piecing together a three-dimensional structure from many kinds of evidence. This is one reason nearby voids are so valuable. When a void is nearby, astronomers can measure not only where galaxies are, but also how they move. Those motions reveal the underlying gravitational landscape. A galaxy moving slightly faster or slower than expected may be responding to a nearby cluster, filament, or void. By collecting many galaxy distances and velocities, projects like cosmic flows reconstruct the nearby cosmic velocity field, almost like mapping currents in a dark ocean. The galaxies become floating markers. Their motions reveal the shape of the water. In this case, the water is the gravitational field of matter and emptiness around us. The local void becomes clearer in that kind of map. Its boundary can be traced not just by where galaxies are missing, but by how nearby galaxies move. Dense regions and empty regions together explain the flow. This is important because a void is not only a place on a map, it is a dynamic feature. It changes the movement of surrounding matter. It participates in the large-scale motion of galaxies. It helps define the cosmic environment in which the Milky Way lives. There are many other named voids throughout survey maps. The northern local void, the southern local supervoid, the sculptor void, the microscopium void, and more catalogued underdense regions found in galaxy surveys. Some names are tied to constellations, some to survey geometry, and some to local structure. But for every famous named void, there are many more identified by catalogues rather than memorable names. Large surveys can contain thousands of voids, each one defined by galaxy distributions, redshift measurements, and void-finding algorithms. Most do not receive dramatic nicknames. They sit quietly in data tables, doing useful scientific work without ever becoming the great anything. The named voids, though, help us tell the story. They give the emptiness a geography. They remind us that the cosmic web is not just an abstract pattern in simulations. It is a real map, with nearby hollows and distant basins with edges, passages and influences. The local void sits beside us. The Boötes void became famous for its striking lack of galaxies. The Eridanus supervoid lies along a line of sight connected to one of the most discussed anomalies in the microwave background. The KBC void raises the possibility that our larger region may be underdense enough to affect local cosmological measurements. Each one gives emptiness a name, and once something has a name, we tend to notice it more carefully. There is something soothing about that, in a way. The universe is not one endless, anonymous dark. It has neighbourhoods, it has regions with different characters. Some are dense and busy, full of galaxy clusters and hot gas. Some are sparse and quiet, with only a few faint galaxies across huge distances. Some are nearby enough to influence our motion. Some are far away enough to test our models of the early universe. The voids are not all the same, and neither are the places around them. The universe has geography on a scale so large that a map becomes an act of patience. If you imagine zooming out from Earth, the layers appear slowly. First, Earth itself, bright and small, then the solar system, then the Sun's neighbourhood, then the Milky Way, then the local group. Keep going, and the nearby galaxy distribution begins to form a sheet. Nearby, the local void opens like a wide, underdense basin. Beyond that are other voids, clusters, filaments, and walls. The map becomes less like a random scatter and more like terrain. You can almost imagine valleys, ridges, plains, and cities of light, although the distances are so large that every earthly comparison eventually gives up and goes to bed. This is the empty neighbourhood around us, not empty in the absolute sense, but underdense, structured, and connected. The local void is part of our cosmic surroundings. The named voids beyond it help us understand how unusual or ordinary our region may be. The larger proposed local underdensity raises questions about how measurements from our neighbourhood compare with the whole universe. And the distant named voids remind us that emptiness can be large enough to leave subtle marks on light travelling across the cosmos. By the time we reach the question of ancient voids, we're no longer only asking where the galaxies are missing. We're asking why the universe has this pattern at all. Why are there clusters here, filaments there, walls stretching across the dark, and enormous open regions between them? Why did matter gather into a web instead of remaining smooth? Why did some places become crowded with galaxies while other places became so sparse that we call them voids? These questions carry us back, not to a time when the voids already existed as great empty rooms, but to a time when their seeds were almost unimaginably small. The cosmic voids we map today were not born as giant hollows. They began as tiny differences in density in the very early universe, small departures from perfect smoothness that gravity, expansion, dark matter, and time slowly magnified into the vast web we see now. The universe, when it was young, was not full of galaxies. There were no stars, no planets, no galaxy clusters, no Bhuta's void, no local void, no sleepy person listening to a calm science video and wondering whether the universe has too much storage space. In the first hundreds of thousands of years after the Big Bang, the universe was hot, dense, and filled with particles and radiation. Light could not travel freely in the way it does now because it kept scattering off charged particles. Then, about 380,000 years after the Big Bang, the universe cooled enough for electrons and nuclei to combine into neutral atoms. Light was finally able to travel across space. That ancient light is what we now observe as the cosmic microwave background, the faint afterglow of the early universe. The cosmic microwave background is often described as a baby picture of the universe, and like many baby pictures, it looks smooth at first glance. But when measured carefully, it contains tiny temperature differences. These differences correspond to tiny density differences in the early universe. Slightly denser regions would eventually become the places where matter gathered more strongly. Slightly less dense regions would eventually become the roots of voids. So when we talk about ancient voids, we do not mean that today's huge empty regions were already sitting there, fully formed, when the universe was a baby. We mean that the early universe already contained the faint unevenness that would later grow into them. This is one of the deepest reasons cosmic voids matter. They are not random gaps that appeared late in cosmic history. They are the grown-up shapes of ancient underdensities. They preserve in their sizes, shapes, and distribution information about the universe's earliest conditions. The galaxies and clusters are one side of that history. The voids are the other. Dense seeds grew into crowded structures. Underdense seeds grew into empty basins. The cosmic web is the mature result of both processes. Imagine a very smooth sheet, with only the faintest wrinkles in it. At first, the wrinkles are barely visible, but now imagine that over a very long time the raised parts keep rising and the low parts keep sinking. Eventually a landscape appears. Hills, valleys, ridges, basins. The cosmic web grew in a somewhat similar way. Although the sheet is space-filled with matter, the wrinkles are early density fluctuations, and the landscape is made of galaxies, dark matter, and voids. The raised parts became the dense structures. The low parts became voids. The early universe did not need to begin with dramatic holes. It only needed tiny differences and enough time. Dark matter was central to this process. Because dark matter does not interact with light the way ordinary matter does, It helped form the gravitational scaffolding of the cosmic web. Ordinary matter later fell into those dark matter structures, cooled, formed gas clouds, stars, and galaxies. In places where dark matter density was low, fewer halos formed, fewer galaxies appeared, and the voids opened wider. This means that the visible voids between galaxies are rooted in invisible dark matter under densities. The ancient voids are not only gaps in the galaxy map. They are part of the dark matter map that began growing from the earliest fluctuations. This is why simulations are so important. When cosmologists create a simulated universe using the early density pattern, dark matter, gravity, expansion, and the known ingredients of the standard cosmological model, the cosmic web forms naturally. Filaments appear, clusters grow, voids open between them. The result looks, in a broad statistical sense, like the universe we observe. That agreement is one of the great successes of modern cosmology. It tells us that the large-scale pattern of galaxies and voids is not a mystery separate from the Big Bang. It is one of the Big Bang's long consequences. But voids do more than confirm the general picture. They help test the details. One important detail is the shape of the universe. In everyday speech, shape usually means something you can draw on paper. Round, flat, curved, lumpy, perhaps a little potato-like if we're discussing certain asteroids. But in cosmology, the shape of the universe can mean its large-scale geometry. Is space flat, positively curved like the surface of a sphere in higher dimensional analogy, or negatively curved like a saddle in that same mathematical sense? Measurements of the cosmic microwave background show that the observable universe is very close to flat, but galaxy surveys and large-scale structure give additional ways to test geometry. Voids can help because their shapes are affected by how we convert observed redshifts and angles into distances. If we assume the wrong cosmological model, a population of voids may appear stretched or squashed along our line of sight. This idea is related to the Alcock-Pazinski test. In simple terms, if objects or structures should be statistically round on average, but our map makes them look distorted, the distortion may reveal something about the expansion history and geometry of the universe. Individual voids are not perfect spheres, of course. They are lumpy, stretched, and influenced by nearby structures, but across many voids the average pattern can be useful. The emptiness becomes a ruler, not a ruler you would keep in a desk drawer, but a cosmic one built from statistics. Voids also reveal the universe's expansion history. Because they are underdense, they respond strongly to the balance between gravity and expansion. In denser regions, gravity gathers matter and can bind structures together. In voids, there is less matter to resist the general expansion, so voids tend to grow relative to the cosmic web around them. Their walls become more defined as matter moves toward filaments and clusters. Their interiors become emptier. This growth depends on the expansion history of the universe. And that brings us to dark energy. Dark energy is the name we give to whatever is causing the expansion of the universe to accelerate. It is not well understood. It may be a cosmological constant, a property of space itself. It may be something more dynamic. It may point toward new physics we have not yet found. Voids are useful here because they are low-density environments, where the effect of cosmic expansion is especially visible in the structure's evolution. By studying the abundant sizes, shapes, density profiles, and motions around voids, scientists can test models of dark energy. A universe with one kind of dark energy may grow voids slightly differently from a universe with another kind. The differences can be small, but with enough voids and careful measurements, small differences become evidence. The fate of the universe is tied to this question. If dark energy behaves like a cosmological constant, the expansion will continue accelerating. Distant galaxies not bound to us will move beyond reachable horizons over immense timescales. Clusters and groups that are gravitationally bound may remain together, while the spaces between large structures grow wider. Voids will become larger in a relative sense, and the cosmic web will become more isolated into bound islands separated by expanding emptiness. That does not mean galaxies themselves are being torn apart in the ordinary future predicted by the standard model. It means that on the larger scales the separation between unbound structures grows, the universe becomes colder, darker, and more spread out. If dark energy changes over time, the fate could differ. It might weaken, it might strengthen. In extreme speculative cases, expansion could become so strong that even bound structures are affected, though that is not the standard expectation. Voids help test these possibilities because their growth is sensitive to cosmic acceleration. They are like slow gauges embedded throughout the universe. They do not point with needles or flash warning lights. They simply have the sizes and shapes they have, and those features carry information about how expansion has worked over billions of years. Voids also probe hidden forces, or at least hidden ingredients that behave like forces in the equations we use. Dark matter is one. Dark energy is another. Gravity itself may be another question. General relativity has passed many tests, but scientists still ask whether it remains exactly correct on the largest cosmic scales. Some modified gravity theories try to explain cosmic acceleration without dark energy, or with a different relationship between matter and space-time. These theories often hide their differences in dense environments, where screening mechanisms make gravity look nearly like general relativity. But voids are low-density environments. Screening can be weaker there. That means voids may be one of the best places to search for subtle deviations from Einstein's theory. This does not mean voids have strange new forces swirling inside them like invisible weather. It means their low-density nature makes them sensitive testing grounds. If gravity behaves slightly differently when matter is sparse, voids may reveal it through their shapes, their density profiles, their galaxy flows, or their lensing signals. A crowded cluster is full of complicated astrophysics, hot gas, mergers, and energetic black holes. A void is cleaner. Not simple, but cleaner. Sometimes the universe's quiet places are where its rules can be heard more clearly. Neutrinos also leave faint traces. These tiny particles are extremely light and fast-moving, and they affect the growth of cosmic structure in subtle ways. Because they do not clump as easily as cold dark matter on small scales, they can slightly suppress structure formation. This can affect the abundance and properties of voids. By combining void studies with galaxy clustering, cosmic microwave background measurements, and other data, scientists can place limits on the total mass of neutrinos. Once again, the void becomes a tool for studying something almost invisible. The emptiest places help weigh some of the lightest particles. There is a remarkable pattern in all of this. The brighter and denser parts of the universe tell us many things. Galaxies tell us how stars formed. Clusters tell us how matter gathers. Nebulae tell us how gas becomes light. Black holes tell us how gravity behaves in extreme places. But voids tell us something different. They tell us how the universe grows where matter is scarce. They show us how the early underdensities developed. They help test the geometry of space, the expansion history, dark matter, dark energy, gravity, and neutrinos. They are not empty of information. They are full of the consequences of missing matter. The ancient nature of voids also helps us see the Big Bang in a new way. The Big Bang was not an explosion into empty space, with matter flying outward from a central point. It was the hot, dense, early state of the whole observable universe, followed by expansion and cooling. The seeds of structure were present as tiny fluctuations everywhere. Over time, those fluctuations grew. So when we look at a cosmic void today, we are not looking at something separate from the Big Bang. We are looking at one of the Big Bang's long shadows, one of the regions where the early universe was slightly less dense, and gravity slowly amplified that small difference into a huge open basin. In that sense, a void is a kind of memory. Not a memory in a mind, but a physical record. It remembers the initial conditions through its existence. It remembers dark matter through its invisible profile. It remembers expansion through its growth. It remembers surrounding structures through its shape. It remembers gravity through the motion of galaxies around it. It remembers dark energy through the way it has widened over cosmic time. A void is not a blank page. It is a page written faintly, with ink that becomes visible only when we learn how to read absence. And we are learning. Modern surveys such as DESI, Euclid, and other large galaxy mapping projects are increasing the number of known voids enormously. With more galaxies mapped across larger volumes, astronomers can identify more voids, measure them more accurately, and compare them with simulations in greater detail. Weak gravitational lensing can help measure the dark matter deficits inside them. Redshift space distortions can reveal galaxy flows around them. The cosmic microwave background can show subtle imprints from the largest voids through lensing and temperature effects. Each method adds a layer to the map. The void becomes less invisible, even while remaining dark. Still, we should keep a little humility nearby, perhaps folded gently beside the blanket. Voids are difficult to define, their boundaries are fuzzy, their shapes are irregular. Different surveys and algorithms can identify them differently. Some named supervoids are debated in size, depth, and significance. Some proposed connections to cosmic anomalies remain uncertain. The science is powerful, but not finished. That is not a weakness. It is part of what makes voids interesting. They sit at the edge of what our maps can tell us, and they ask for better maps. So what do cosmic voids reveal about the universe's shape, fate, and hidden forces? They reveal that the universe began with tiny unevenness, not perfect smoothness. They reveal that gravity turned those tiny differences into a web of dense structures and empty basins. They reveal that dark matter built the invisible scaffolding beneath the galaxies. They reveal that dark energy and cosmic expansion influence the growth of underdense regions. They reveal that the geometry of the universe can be tested by the apparent shapes of large structures. They reveal that modified gravity, neutrinos, and other hidden ingredients may leave their quietest clues where matter is thinnest. And perhaps most gently of all, they reveal that absence is not the opposite of structure. Absence is part of structure. We began this journey by imagining voids as the quiet rooms of the cosmos. Now those rooms are no longer empty in the simple sense. They have histories. They have edges. They have dark matter profiles, faint galaxies, motions, and connections to the earliest light we can see. Some are small and squeezed by cosmic crowds. Some grow inside greater emptiness. Some are large enough to challenge the imagination. Some sit near our own local sheet of galaxies, shaping the motion of our cosmic neighbourhood. And all of them, from ordinary galaxy voids to supervoids and dark matter hollows, belong to the same great web. If you are still awake, just barely perhaps, you might picture the universe one last time from far away, not as a flat black sky with stars scattered on it, but as a vast three-dimensional network. Galaxies gather like glowing cities. Filaments stretch like long roads through darkness. Clusters shine at the crossings, and between them open the voids, broad and quiet, carrying the memory of the universe's first tiny differences. The emptiness is not wasted space. It is the room that lets the web exist. It is the contrast that lets the pattern appear. And here we are, on a small planet, inside one galaxy, near one local underdense region, using maps, light, mathematics, and patience to understand spaces so large that even light crosses them slowly. That is a comforting thought, in its own strange way. We are small, yes, but we are not disconnected. The atoms in us, the galaxy around us, the voids beyond us, and the ancient light behind all of it are parts of one long story. The universe made crowded places and quiet places. It made stars and gaps between stars, galaxies and gaps between galaxies, questions and the patience to follow them. So, As the thought of these great cosmic voids settles into the dark, let the scale become soft rather than heavy. Somewhere beyond the Milky Way, the local void opens beside our neighbourhood. Farther away, named voids and unnamed voids fill the web. Deeper still, the ancient seeds of those voids are written in the afterglow of the Big Bang. And right here, in this small moment, you can rest without needing to hold the whole map at once. The universe has plenty of room. More room than we can imagine. More quiet than we can measure. And in all that quiet, the story of everything is still gently taking shape. If this journey through the universe's empty places brought you a little calm, or gave your mind somewhere wide and quiet to wander, I would be very grateful if you liked the video, subscribed, and shared this sleepy corner of science with someone else who might enjoy drifting through the cosmos at a slower pace. For now, let the galaxies gather where they gather, let the voids open where they open, and let your thoughts loosen their grip on the day. Sleep well, fellow traveller, here among the bright things, the dark spaces, and the soft silence between them.